Babylon's Base 60 Legacy. There's a kind of quiet magic hiding in your day, in the ticking of a clock, the shape of a circle, the way you glance at your watch and say, "Give me 5 more minutes." You don't think about it. You don't have to. But somewhere beneath those numbers, the 60 seconds, the 12 hours, the 360 degrees, is the ghost of a civilization long gone. Not just ancient, old Babylon. Over 4,000 years ago, along the wide, slow rivers of Mesopotamia, people began carving symbols into soft clay, not just to trade grain or track the moon, but to think in numbers. And when they did, they made a choice. Not one they argued about or voted on. Just a choice that stuck. They didn't count by tens, they counted by 60s. It sounds strange at first. 60? Who would choose that? 10 makes sense. 10 fingers, 10 toes, easy. But look closer. 60 is smooth, flexible, generous. It divides by 2, by 3, by 4, 5, 6, all the way up to 30. Few numbers share that gift. 60 is a kind of quiet diplomat in the world of numbers, able to split itself easily, cleanly, into neat pieces. 12 parts, 6 parts, 2/3, 1/5. To a civilization that didn't have calculators, decimals, or zero, this mattered a lot. So they built with 60. They measured with it. They passed it on. From clay tablets to star charts, from water clocks to trade records, their number system, this base 60, seeped into time itself. And long after Babylon fell, the numbers stayed. Not because someone made a law, but because it worked, because it was convenient. And over time, the convenient becomes the invisible. When you say it's 3:30, you're speaking Babylonian. When you angle a triangle 90 degrees, you're bending space with their math. When you count 60 seconds in a minute, or 360 degrees around a circle, you're echoing the minds of people who watched the skies, tracked Venus, and carved their thoughts in cuneiform, never knowing we'd still be listening. That's the strange, soft power of math. It doesn't shout. It lingers, sometimes in stone, sometimes in the way you check the time, not knowing the hands on your watch are reaching back through 4,000 years to touch the minds of those who counted differently, and in doing so, changed everything. The Lebombo Bone, the first math tool, before there were books, before paper, or writing, or even the wheel, there was a bone. Rough, weathered, cut by hand, not polished, not perfect, but precise in its own quiet way. It's called the Lebombo Bone, and it might just be the oldest known math tool in human history. It doesn't look like much. A piece of baboon fibula, maybe the size of your hand. It's cracked in places, darkened with time. But along one edge, something catches your eye. Notches, tiny grooves carved deliberately. 29 of them, each one etched with care, like a quiet whisper from the deep past. Discovered in a cave between South Africa and Swaziland. This bone is believed to be over 43,000 years old. That's older than the pyramids, older than agriculture, older than most things we call history. And yet, someone somewhere picked up this bone and counted, not just once, not randomly, but with pattern, with rhythm, with purpose. Why? We don't know for sure. But the beauty of early mathematics is that it didn't start in universities. It started in need, and in pattern. Maybe it was to track the moon. The notches line up almost exactly with a lunar cycle, 29 days. Maybe someone, 43,000 years ago, was watching the sky, marking time through shadows and light. Or maybe it was for something simpler. Cycles of the body. Some anthropologists believe it could have been used to track a woman's menstrual cycle. If that's true, then the very first math tool wasn't a device of conquest or trade, but of care, of understanding a body, a rhythm, a life. Isn't that something? We often think of math as cold, clinical, equations on chalkboards, numbers in textbooks. But this bone, this quiet artifact from before history, reminds us that math didn't begin with answers. It began with attention, with someone noticing, this happens again and again. Let me mark it down. Let me remember. Let me count. Not because they needed to pass a test, not because they wanted to be a mathematician, but because they wanted to understand their world. The Lebombo Bone was found near other artifacts, early tools, cave drawings. It was a time of survival. People hunted, gathered, watched the seasons closely. Every detail mattered, and the more you notice patterns, the more you begin to predict. You stop reacting. You start preparing. That's what math is in its rawest form. Not numbers for the sake of numbers, but numbers for the sake of knowing. And there's something quietly beautiful about that. No one taught the maker of the Lebombo Bone how to count. There was no curriculum, no classroom, only instinct, observation, repetition. That's how most early math likely began. Not in the abstract, but in the intimate. How many days since it rained? How many animals did we trap last moon? How many berries can I carry before I drop one? These were the first math questions, not what is X, but when, how many, how long. And so someone picked up a bone and started carving. One notch, then another, until a pattern emerged. What makes this small artifact so special isn't just that it's old, it's that it shows us the seed of something massive. From 29 notches on a baboon bone, we would one day reach calculus, code, quantum physics. But the root remains the same. A question, a cycle, a count. It also makes you wonder how many other tools like this were lost. Was the Lebombo Bone the first of its kind, or just the first we found? How many unnamed people watched the sky, or tracked their breath, or counted the days between floods, quietly doing math, long before anyone called it that? We may never know, but the Lebombo Bone survived, and in its silence, it still speaks. It tells us that mathematics was never just about rules or rigid systems. It was about meaning, and rhythm, and pattern, and memory. So the next time you open a calendar, or mark a date, or track your steps on a glowing little screen, remember you're continuing something that began in a cave 43,000 years ago, with a bone, and a mind, and a question. Not much has changed. Egypt's art of unit fractions. There's something quietly humbling about fractions. Maybe it's the way they seem to split the world into smaller, manageable pieces, like gently cracking a loaf of bread and handing half to someone beside you. But for the ancient Egyptians, fractions weren't just a way to share, they were a way to see. Not as we do today with decimals and numerators stacked neatly over denominators, but with a language made entirely of unit fractions, fractions where the top is always 1. 1/2, 1/3, 1/5. That was their grammar of division. That was their rhythm. To them, every part was always a piece of 1. And when they needed to express something like 3/4 or 5/6, they didn't write it that way. They broke it down, carefully, elegantly, like 3/4 becomes 1/2 plus 1/4. 5/6 becomes 1/2 plus 1/3. Always the sum of distinct unit fractions, never repeating, never doubling up. It wasn't clunky or strange to them. It was natural, ritual, even. Because the world, at least as they saw it, was not made of repeating decimals and abstract symbols. It was made of shares, of portions, of fairness, grain rations, bread loaves, temple offerings, all divided by hand, all counted by eye. The math had to serve the human world, and the human world is filled with people who remember one thing at a time. So the Egyptians made a system where every part could stand alone, a system where even the smallest sliver had dignity. You can see it clearly in the Rhind Mathematical Papyrus, a 3600-year-old scroll written by a scribe named Ahmes. He wasn't a philosopher, not a prophet, just a man copying numbers with care. But what he copied has lasted longer than empires. On that papyrus, Ahmes records dozens of calculations involving fractions, and all of them honor this strange, consistent rule. Only unit fractions. Always. And it raises a question. Why? Why go through the trouble? Why insist that 2/3 can't just be 2/3, but must be written as 1/2 plus 1/6? It's easy to dismiss it as primitive, or inefficient, or quirky. But maybe it wasn't about ease. Maybe it was about intuition. Maybe it's easier, when bartering in a market or preparing grain for a family, to think in terms of single familiar portions. I'll give you 1/6, then 1/2. Each one has a weight, a meaning. It's not abstract, it's personal. And beyond practicality, there's something philosophical here too. The Egyptians believed in Ma'at, a concept deeper than order or justice. It was about harmony, the balance of all things, the symmetry of nature, and the rightness of truth. And in this light, their fractions take on another meaning. To express a number not with messiness or shortcuts, but by unfolding it into simple, indivisible pieces, that was a gesture of Ma'at. One is whole, and everything else is only a portion of it. What a quiet, beautiful thought. You can almost imagine a scribe sitting under low light, stylus in hand, not just recording math, but respecting it. Not forcing numbers to obey a system, but letting them unfold naturally, piece by piece, until they reveal their shape. In some of the older texts, you'll find special symbols for the most common fractions. They had a dedicated sign for 1/2, for 1/3, for 2/3, a symbol that was rare because it wasn't a unit fraction, but still sacred because it came up so often. Beyond that, every other fraction was spelled out by combining unit parts. Sometimes the combinations were clever, sometimes they were awkward, sometimes they were long, but always, they followed the pattern. Even when faced with a complex number, like 4/7, they'd break it into something like 1/2 plus 1/14. Clean, respectful, consistent. And over time, scribes developed tables to help with this. Charts of decompositions, guides for breaking any number into unit parts. Not unlike how we might reach for a calculator. But there's something deeply human about their method. It wasn't about precision for its own sake. It was about understanding, about turning any problem into recognizable pieces. And maybe that's something we've lost. In our obsession with speed and efficiency, we often forget that math once lived closer to the ground. It was spoken, gestured, negotiated, and in Egypt it was always done with an eye toward unity. Even their fractions reflected a worldview that everything begins from one, and everything can return to it. So the next time you see a fraction like 3/4 or 5/8, imagine someone thousands of years ago taking the time to listen to it, to break it down, not out of compulsion, but out of reverence. What are its parts? How can it be understood? What does it want to become? That was the art of Egyptian mathematics. Not just numbers but relationships. Not just answers, but rituals of balance. Euclid's Elements, the 2,000-year textbook. There's a strange kind of quiet that surrounds the name Euclid. Not the loud, disruptive genius of revolution, not the tortured artist of formulas, but something different, steady, clean, almost serene. When you hear the name, you don't picture wild hair or dramatic theorems. You picture order, simplicity, a compass drawing a perfect circle, a straight edge slicing clarity through chaos. And maybe that's why his work lasted. Euclid's Elements is not a book you read cover to cover. It's not emotional or dramatic. It doesn't demand attention. It just stands, like stone, like geometry itself, unmoving, unshaken, quietly sure of what it is. And it has been standing for over 2,000 years, long before the printing press, long before Newton, before Galileo, before algebra found its name. Elements was already there, copied by hand, translated into Arabic, studied in monasteries, carried across deserts, packed into ships, and eventually printed more than any book besides the Bible. A textbook, yes, but something more. A skeleton for reason, a blueprint for thinking, a calm voice whispering across millennia. Begin with definitions, then axioms, then build. To understand what Euclid did, you have to understand what he didn't do. He didn't invent geometry. That came long before, drawn in the sand by Egyptians, measured on clay tablets by Babylonians, traced in the stars by early astronomers. Humans have always measured things: land, angles, time, the heavens. What Euclid did was different. He gathered, he organized, he removed everything uncertain, everything sloppy or assumed. He took geometry, the raw, useful tool of builders and surveyors, and turned it into a language of truth. He started with just 5 postulates: that you can draw a straight line from any point to any point, that a line can be extended forever, that you can draw a circle with any center and radius, that all right angles are equal, and then, the 5th, that if 2 lines are cut by a third, and the angles inside add up to less than 2 right angles, those lines will eventually meet on the side where the angles are small. It's the messiest of the 5, the awkward one. But he needed it to hold the rest together. And with just those 5, he built everything else: triangles, parallelograms, the Pythagorean theorem, the golden ratio, the nature of prime numbers, the structure of proportions. Like laying bricks with surgical patience, Euclid built a tower of logic, each statement following cleanly from the last. No gaps, no assumptions, just a clear, deliberate climb from the simplest ideas to the deepest conclusions. But Elements is not famous just because it's old. It's famous because of how it thinks. It doesn't rush. It doesn't persuade with charisma or emotion. It persuades with clarity. It says, if this is true, and this is true, then this must follow. And in that it teaches more than geometry. It teaches a way of seeing, a way of being. Imagine being a student in ancient Alexandria, sitting on stone steps, a wax tablet in your lap. A teacher draws a triangle in the dust. From 2 points, they say, a straight line may be drawn. And just like that, you're pulled into a world where every shape, every line, every truth flows from the one before it. There are no calculators, no equations, just reasoning. Just space and lines and thought. Now imagine that same triangle drawn 1,000 years later, in a candle-lit monastery in northern Europe, or on a silk scroll in an Arabic library, or in a Renaissance classroom, just before the birth of calculus. It's still the same triangle, still the same truth, still the same logic, whispering across time. What's strange is that Elements doesn't tell you how to use math. It doesn't care if you want to build a bridge or a temple. It doesn't teach you formulas for speed or curves or force. It teaches you how to think precisely, how to hold one idea still while turning another gently in your hands. It doesn't shout. It doesn't bend to culture or context. It waits, and in waiting it invites. So why does it matter? Why care about a book of diagrams and proofs when we live in a world of quantum mechanics and AI? Because logic doesn't expire. Because clarity doesn't go out of style. Because long before computers, before data, before machines, we were trying to make sense of things. And Elements gave us a way to start. It taught us how to argue without shouting, how to reason without violence, how to build from nothing but certainty. And that might be the rarest thing of all. If you ever feel overwhelmed by noise, by opinion, by endless contradiction, there's something almost medicinal about reading Euclid, something grounding. A triangle is still a triangle. A circle is still a circle. And even after 2,000 years, a quiet mind can still trace a line and know where it leads. The Rhind Papyrus, ancient algebra. There's a scroll, faded, brittle, and over 3,500 years old, resting in the British Museum. It doesn't look like much at first glance. Just lines of hieratic script, symbols, columns, but hidden in its fibers is a quiet moment of human thought. A man trying to make sense of the world using numbers. His name was Ahmes, a scribe, not a priest, not a king. Just a man with ink and curiosity. He didn't write the ideas himself. He tells us that he was copying older work from another time, another thinker. But still, he copied with care. And that care made something last. Today we call it the Rhind Mathematical Papyrus. It's named after the Scottish collector who bought it in the 1800s, but long before that it sat unrolling quietly under Egyptian sun, waiting. This isn't just a list of math problems. It's a glimpse into how ancient minds saw numbers, not just as tools, but as companions. You can feel the patience in the way things are explained, step by step, as if someone is standing beside you saying, "Let me show you how this works." Let's pause for a moment. Try to picture the world of Ahmes. No calculators, no chalkboards, no equals sign, no equals sign. That wouldn't be invented for nearly 2,000 years. And yet, here on this scroll, we see something astonishing. A problem, a mystery with a missing part, a question that sounds strangely modern, a quantity. Its seventh is added to it. The result is 19. What is the quantity? This, in essence, is algebra. A hidden number, a relationship, a mind asking what must this unknown be if the parts behave this way. In modern terms, we'd call it solving for x. But Ahmes didn't use letters. He used reason. He guessed, checked, adjusted. A method we now call the method of false position. He'd try a number, say, 7. Add its seventh, 7 plus 1 equals 8. Too low. Try again. Guess 14. Its seventh is 2. 14 plus 2 equals 16. Still low. Try 16. 1/7 of 16 is about 2.28. 5. 16 plus 2.28. 5 is a bit more than 18. Closer. Eventually he lands on 16 3/4. Because 1/7 of 16.75 is 2.392857. Add that and you get 19. There it is. Solved. No variables, no formal notation, just mind and method. What's beautiful is not the complexity, it's the clarity, the transparency of thought, because before there was formal math, there was something more delicate, understanding. You'll notice something gentle about the problems in the Rhind Papyrus. They're not grand or cosmic, no proofs of the universe, no deep abstraction. Instead, they ask things like, how much grain should be given? How many loaves are shared among men? If a part is added to itself, and we know the total, what was the part? Math as a tool, but also math as a mirror, reflecting trade, labor, sharing, justice. Math in the hands of Ahmes wasn't cold, it was intimate. This was algebra without algebra, logic without symbols, equations without equal signs. And yet the human impulse behind it is exactly the same as yours. You've probably solved a puzzle like this before, not on papyrus, but maybe balancing your time, or guessing how long something will take, or splitting a bill with friends. That same quiet movement of thought, what number would make this true? That is what lives in the Rhind Papyrus. Even in ancient Egypt, there was uncertainty, and mathematics, even then, was a way to find steadiness, to bring the unknown into the light, to say this is what we know, now let's find the missing part. Sometimes we think of history as layers buried in time, but sometimes it's more like looking into still water, noticing our reflection in someone else's ideas. Ahmes didn't know what algebra would become. He couldn't have predicted graphs or functions or calculus. But in writing those lines, carefully, patiently, he was doing something timeless. He was trying to understand. And now, centuries later, when you hear the word algebra, you might think of chalk on a board or a textbook in school. But maybe for a moment, you'll remember that it started here. In ink and papyrus, in sand and silence, with a scribe who asked gentle questions and trusted numbers to answer. Liu Hui and the shape of the circle. Imagine a circle, not drawn on paper, not glowing on a screen, just the idea of it, perfect, infinite, smooth, a shape that never begins and never ends. Now imagine trying to measure it. Not just its outline, but the relationship between that outline and the distance across. The ratio of the circumference to the diameter. Today we call that number pi. But there was a time long before calculators, before decimals, before even the symbol itself, when people still wondered, how big is the circle really? And how would you know? Let's go back almost 2,000 years. China. The year is 263 CE. A mathematician named Liu Hui is sitting with ink and brush, staring at a problem that still feels familiar today. How do you find the value of pi? He doesn't call it pi. He doesn't think in Greek letters. But he understands the question, how does the distance around a circle relate to the distance across it? And Liu Hui, like many mathematicians of his time, turns to something simple: polygons. A polygon is not a circle, it's a compromise, but it's a useful one. If you draw a hexagon, 6 sides inside a circle, it's easy to see that its edges hug the curve. The more sides you add, the closer the shape gets to becoming smooth. A 12-sided shape is better. 24 sides better still. 96 sides. Now we're getting somewhere. Liu Hui didn't invent this idea. Archimedes, centuries earlier in Greece, had used a similar method, but Liu Hui took it further. More precise, more careful, more beautiful. He began with a hexagon. Then he doubled the number of sides, over and over. Each time, the polygon fit the circle more tightly, and the estimate for pi grew sharper. He calculated carefully, methodically. He didn't guess, he didn't assume. He used geometry, logic, and a calm kind of patience that feels almost meditative. Pause here. This is not about numbers flying across a blackboard. This isn't a race. What Liu Hui shows us is something slower, a kind of quiet reasoning. Not chasing an answer, but approaching it gently, from all sides. As the number of sides grew, so did the elegance of the method. Instead of trying to find pi directly, he looked at what he could measure, the perimeter of the polygon. And because the polygon sat inside the circle, that perimeter was always less than the circle's circumference. That gave him a lower bound. And then he placed a polygon outside the circle. Same number of sides. Now the perimeter was more than the circle's. That gave him an upper bound. The truth of pi lived in between. A number, caught between two limits. At 96 sides, Liu Hui found his answer, pi rho 3.1416, astonishingly close. For a time before decimal systems, before trigonometry, before calculus or algebra. But Liu Hui didn't just stop with a number. He explained why his method worked. He spoke of the shrinking distance between the polygon and the curve. He hinted at something that wouldn't be formalized for centuries, the idea of a limit. That as the number of sides increases toward infinity, the polygon becomes the circle. It's not there yet, but it's always getting closer. Each step narrowing the gap, not by force, but by refinement. This is not brute mathematics, it's grace. And maybe there's something quietly profound in that. Liu Hui didn't need to know the final value of pi. He only needed to know how to approach it. Over time, through process, with clarity and care. In a world of rough tools and uncertainty, he found a way to shape precision out of approximation. Not by reaching for the unreachable, but by drawing ever closer. A lesson, perhaps, not just for math, but for life. That what matters is not the leap, but the path. The way we move toward understanding. So when we think of pi, we might picture endless decimals, 3.14159 and on. And on and on and on. But maybe we could also remember a scholar, 2,000 years ago, folding more and more sides into a shape, quietly watching it curve, and smiling as it nearly becomes a circle. Almost but not quite. Close enough to glimpse the infinite. Close enough to say, I see you. And maybe that's enough, for now. The birth of zero in India. There's a strange kind of beauty in nothing. Not the empty kind. Not the absence of meaning. But the quiet presence of space. The silence between sounds. The stillness before thought. A pause. A placeholder. A symbol that means there is nothing here. And that matters. That's what zero is. A shape. A concept. A boundary. But it didn't always exist. You might think of numbers as something eternal. Always there waiting to be discovered. But zero wasn't always part of the world's vocabulary. For a long time, people counted without it. They built cities, mapped stars, traded goods, told time, without ever needing to say nothing. And yet it was in India, over 1,000 years ago, that someone finally gave nothing a name. But before we get there, let's pause for a moment. Look around your life. There are zeros everywhere. In clocks, calendars, bank accounts, phone numbers, in the math you learned or avoided. And even if you've never thought much about it, zero shapes the way you understand value, position, possibility. The idea that nothing can be written, placed, and calculated. That's more than clever. It's revolutionary. But revolutions don't start with fanfare. They begin in silence, with small shifts, with people asking quiet questions, ones no one else thought to ask. In ancient India, mathematics wasn't just about measurement. It was about meaning, about pattern, about the search for harmony between the physical and the eternal. The stars moved in rhythm. The planets danced, and numbers weren't just tools. They were reflections of a deeper truth. So it's not surprising that it was here, somewhere between temples and trade routes, between poets and scholars, that zero was born. The concept began softly, as a mark, a dot, a placeholder in the sand. In earlier systems, like Roman numerals or Egyptian hieroglyphs, there was no real need for zero. They didn't have positional notation, the idea that the position of a digit changes its meaning. But the Indian numeral system did. It worked like the one we use today, place-based, base 10. That meant something powerful. The difference between 1 and 10 wasn't just an extra line, it was a space being filled. A 1 followed by. Something had to hold that space, so they marked it, a dot, a small nothing, and eventually, a round shape, a circle, 0. But that dot meant more than emptiness. It meant presence. It said this space matters. It's not blank, it's a 0. And once that idea took root, everything changed. It wasn't just notation. It became a concept, a number in its own right. Something you could add, subtract, use in equations. It behaved like other numbers. It had rules, and because of that, Indian mathematicians, like Brahmagupta in the 7th century, began to treat it seriously. Brahmagupta was one of the first to write those rules down. He called zero shunya, emptiness. He explained how to add it. A number added to zero is the number itself, how to subtract it, multiply it. He even tried to divide by it, though that part would take more time to fully understand. And suddenly, math had room to breathe. Numbers could stretch further, calculations could scale. The system became elegant, clean, flexible. Without zero, you can't do algebra, or calculus, or digital computation. You can't build modern economics, or computers, or GPS. Zero isn't just a placeholder. It's the silent engine of the entire system. And it started with a question so simple, it's almost invisible. What do we do when there is nothing there? India answered that question with grace. It didn't fear the void. It named it, gave it shape, and then gave it power. From there the idea traveled, through Arab scholars who translated and expanded Indian texts. They called it cipher, which later became zero in the West. And the decimal system spread with it, from east to west, from sand to scroll to screen. But even now, we rarely pause to feel the weight of that nothing. We don't think about how bold it is to make space for absence, to write a mark for what isn't there, to let zero mean something. Because zero isn't cold, it's not hollow, it's potential. It's a breath before the note. It's the pause before an idea forms. And in the Indian tradition, this makes sense. In philosophy, in meditation, in spiritual texts, emptiness isn't a loss, it's a doorway. The absence of form reveals something deeper, consciousness itself. So maybe it's no accident that zero came from a place where silence was honored, where the space between things was part of the pattern. And maybe as we look at our own lives, at the gaps, the pauses, the blank spaces, we can remember what India remembered. Nothing isn't the end. Sometimes it's the beginning. Hipparchus, inventor of trigonometry. There's a kind of quiet that comes when you look up at the night sky. Not just silence, but something older, a stillness that makes you feel very small and very curious. Long before apps or observatories or satellite charts, people stared at those same stars and wondered where they go when no one is watching. And among them, over 2,000 years ago, was a man named Hipparchus. He lived in a time when the Earth was still thought to be at the center of everything. The sky was a dome, the stars fixed like pins in a celestial ceiling. But Hipparchus didn't just look. He measured, patiently, repeatedly, quietly, with no telescope, no modern math, no certainty, just his eyes and his mind. He lived in Nicaea, in what is now Turkey. But it was on the Greek island of Rhodes, under the wide Aegean sky, that he did his most important work. This is where trigonometry began, not in a textbook or a formula sheet, but in the quiet process of trying to understand how the moon moves. At first glance, trigonometry might feel like a cold word, technical, something you meet in school and never quite want to see again. But at its heart, it began with a very human problem. How do you predict the motion of the heavens with no way to go there? How do you measure distance between two things you cannot touch? You build a bridge out of ratios. You let triangles speak for you. Hipparchus was the first person, as far as we know, to create a trigonometric table, a guide to the relationships between angles and chords in a circle. Not sine or cosine yet, that would come later. But the idea was the same. He realized that if you knew one part of a triangle, you could know the others. If you had one piece of the sky, you could find the rest. Like finding the whole puzzle from just one edge. Let's pause here, not to rush past this, but to feel the depth of what that means. A triangle. Simple. 3 sides, 3 angles. But inside it, an entire language for describing space, distance, movement. And this idea, born on a quiet island, with nothing but a sky and a brain to measure it, became one of the most powerful tools we've ever used. You can find trigonometry today in the rhythms of music software, the architecture of buildings, the simulation of light in animated films. Planes fly because we measure angles. Cell towers connect because of line-of-sight geometry. Your phone's GPS talks in triangles every time you ask it for directions. And yet in the beginning, it was just a man with time and wonder. He studied eclipses, not to predict doomsday, but to understand motion. He cataloged over 850 stars, comparing their brightness and position with what earlier astronomers had recorded. And from those differences, he discovered something remarkable. The stars weren't fixed. The sky was not still. Over centuries, the stars shifted, slowly, steadily. A wobble in the Earth itself, something we now call precession. Hipparchus was the first to see it. It's strange to think of him there, tracking invisible movements across time, across the dark. No glory, no great reward, just the need to know. And even now, his name doesn't appear often. No social media presence, no holiday. But look quietly enough, and he's there. In every architectural blueprint, in every astronomy textbook, in every moment a student learns the sine of 30 degrees and doesn't know who to thank. Sometimes history remembers the conquerors, but sometimes, if you're lucky, it remembers the calculators, the patient ones, the watchers. Trigonometry didn't arrive in a thunderclap. It drifted in slowly, on parchment, on ink, in the careful turning of circles and lines. In Hipparchus's hands, triangles became more than shapes. They became tools, clocks, maps. He didn't finish the work. No one ever really does. But he began something that would eventually measure oceans, trace orbits, guide ships, decode signals. And maybe this is what's most beautiful about it all. He didn't invent trigonometry for math's sake. He wasn't trying to solve a standardized test. He was simply paying attention to the world, curious enough to ask, how does the moon know where to go? Why do the stars shift just a little every few centuries? Can I know something real from something far away? And from that quiet question came a language that has never stopped unfolding. Trigonometry didn't begin in a classroom. It began in the sky, with the slow grace of a star's drift, with a triangle drawn in the dark, with a man named Hipparchus, and a simple, persistent need to understand. Al-Khwarizmi and the birth of algebra. There's a quiet kind of magic in the idea that a concept, an invisible tool of thought, can outlast empires. Somewhere in 9th century Baghdad, in a library lit by oil lamps and softened by the rustle of parchment, a man named Muhammad ibn Musa al-Khwarizmi sat with numbers. He wasn't inventing fire or steel or stone. He was doing something stranger. He was teaching the world how to solve for the unknown. And in doing so, he helped invent algebra. The word itself, al-Jabr, comes from the title of his book, Al-Kitab al-Mukhtasar, Hisab al-Jabr, wal-Muqabala, loosely translated as the compendious book on calculation by completion and balancing. It doesn't sound revolutionary at first, but what it contained would echo through time. You may have seen equations like x plus 3 equals 7. Simple enough, solve for x. But behind this little puzzle is a centuries-long inheritance, one that stretches through desert cities, ancient markets, Greek texts, and dusty clay tablets. And it was Al-Khwarizmi who began to shape this inheritance into something structured, something teachable, something that could be passed on. But before we go deeper, let's pause. Most of us were introduced to algebra in school, likely under stress. Memorize formulas, solve for x. Show your work. Somewhere between chalkboards and test papers, the subject became a kind of mental obstacle course. But if you can set that aside, just for a moment, you'll see something different. You'll see that algebra isn't really about letters or numbers. It's about relationships. It's about finding balance. It's about looking at what's visible, then wondering what's missing, and trusting that it can be found. It's a way of thinking that says, even if a part of the picture is hidden, the whole still holds together. You just have to listen. That's the spirit Al-Khwarizmi worked with, not a scramble of variables, but a calm method for revealing what's concealed. He didn't use symbols like we do today. No x, no y, no equals sign. His explanations were written entirely in words. Imagine a math problem spelled out like a paragraph. Long sentences explaining how to manipulate numbers step by step. Add this to both sides, subtract that, take half the root, complete the square. It was mathematics as language, not as code. And that's important, because in Al-Khwarizmi's time, numbers weren't just tools. They were companions in a deeper kind of thinking. His algebra wasn't about crunching, it was about clarity. He gave examples with real-world relevance, inheritance, land division, architecture, not because he was trying to be practical, but because he believed mathematics was for life. Not abstract life, but daily life. Life with questions, life with unknowns. Algebra, in his hands, wasn't a subject. It was a mirror. Let's slow down here. Take a breath and ask yourself, when was the last time you were faced with something uncertain? A decision, a feeling, a situation where part of the story felt missing. That moment when you think, I don't know what to do. That's the essence of algebra, not just in numbers, but in life. To live with the unknown and still try to solve. We don't always know the outcome. We don't always see the full equation, but we try to balance what we can. And that idea, that structure exists beneath uncertainty, is what Al-Khwarizmi gave voice to. His work spread. It was translated into Latin in the 12th century, and that translation carried his influence across Europe. The word al-Jabr became algebra. His name Al-Khwarizmi slowly morphed through years and tongues into a strange echo algorithm. So every time you search, sort, click, and compute, his legacy is there, not just in symbols, but in how we think. Because algebra isn't just a system, it's a shift in perspective. It says that the unknown isn't a threat, it's a starting point. It says that structure can arise from mystery, that we can look at fragments and still find form. Al-Khwarizmi didn't know the future he was building toward. He couldn't have imagined the machines, the graphs, the textbooks with his ideas on every page. But he understood something timeless, that even in a world of incomplete information, we can still try to understand. That the unknown isn't chaos, it's potential. And that a thoughtful mind, given space and time, can uncover what seems hidden. So the next time you see an equation, any equation, don't rush past it. Pause. Not to solve it, not to memorize it, just to remember that someone, centuries ago, believed it was possible to think clearly in the face of the unknown. And that belief, that gentle insistence that mystery can be met with method, is what gave birth to algebra. And that's worth a moment of quiet awe. Where algorithm got its name. There's a word you've heard 100 times, maybe more. It moves invisibly through your life, deciding what you see, what you buy, what you scroll past at midnight when sleep feels far away. The word is algorithm, and most of the time it sounds cold, mechanical, something coded in a glowing room by people who drink too much coffee and don't blink enough. But there's something you might not know. That word algorithm was once a man's name, and before it belonged to machines, it belonged to memory, to ink, to the curve of letters written slowly in desert air. His name was Muhammad Abayan Minsa Al-Khwarizmi, and he lived more than 1,000 years ago. Let's pause there. That name might sound far away from your world, and it is, in time, in language, but maybe not in spirit. Because Al-Khwarizmi was trying to do something we all try to do, in our own quiet ways, make sense of the world. He was born in what's now Uzbekistan, sometime in the 9th century. He worked in Baghdad, at a place called the House of Wisdom. It wasn't a school in the way we think of schools. It was more like a breathing library. Scholars, translators, astronomers, all gathering, not just to learn, but to listen. To texts in Greek, Sanskrit, Persian, to voices long gone, to ideas still echoing. And Al-Khwarizmi, he listened carefully. Then he began to write. One of his most famous books was about solving equations. But it wasn't just filled with numbers. It was filled with instructions, simple step-by-step processes for figuring things out. You want to know how to split an inheritance fairly, how to measure land, how to calculate interest. He didn't just give answers. He gave methods, ways of thinking. The book was called Al-Kitab, Al-Muqta, Fadisab al-Jabr, wal-Muqabala, translated, the compendious book on calculation by completion and balancing. A mouthful, yes, but don't get lost in the title. Because inside was something remarkable, a way to solve problems systematically, not by guessing, not by trial and error, but by following a path, one step then the next. Sound familiar? It should. That's the soul of an algorithm. But the word algorithm didn't appear yet. Not exactly. When Al-Khwarizmi's work was translated into Latin a few centuries later, scholars tried to write his name. But Arabic letters don't line up perfectly with Latin ones. So Al-Khwarizmi became Algorithmi. Then through time and usage, Algorithmi became algorithmus. And finally, algorithm. So every time you hear that word now, on podcasts, in meetings, in the background of your scrolling, you're hearing the faint echo of a name, not a machine, a man. And that changes something, because it reminds us that what we call modern has roots, that even in a world shaped by artificial intelligence and endless data streams, there are fingerprints in the foundation. In Al-Khwarizmi's time, math wasn't a race. It wasn't about being fast or being first. It was about being clear, being fair, being able to explain something so well that even someone who had never seen numbers on paper before could understand. That kind of thinking is harder than it looks. It's not flashy, it's patient. And the beauty of Al-Khwarizmi's work wasn't just in solving equations, it was in showing people how to solve them, in giving them a structure they could trust, a way through confusion, a lantern in the cave. And maybe that's what the best algorithms still try to do. They aren't just lines of code, they're choices, they're design paths. Someone sat down and said, if you start here and go this way, you'll find your answer. Of course, the algorithms we use today aren't always neutral. Some hide things, some reinforce bias, some nudge us in ways we can't quite see. But the original impulse, it came from a good place, from the belief that problems could be made less intimidating, that even the complicated could be made clear, and that clarity was worth working for. So the next time you hear the word algorithm, pause, just for a second. Let it be more than a buzzword. Let it be what it really is. A reminder of a mind from centuries ago, who thought deeply, wrote carefully, and gave the world not just answers, but a way to begin. A name hidden in a system, a human behind the function. Al-Khwarizmi, the man who became the method. Geometry in the Sulba soared us. There's something quiet about ancient knowledge. It doesn't shout, it waits. Etched in verse, tied to ritual, passed down in rhythms long before writing was common. The Sulba Sordas are like that. They aren't textbooks. They weren't trying to teach geometry the way we understand it now. And yet, hidden inside their ritual instructions is some of the oldest geometry ever recorded. Let's begin not in a classroom, but on an open patch of land, thousands of years ago, in what is now India. A rope is stretched, a peg is placed in the earth. Another, and slowly, something takes shape, not just a square, not just a circle, but a space meant for the sacred. A Vedi, an altar, prepared with precision. This was the world of the Sulba Sordas. Sulba means cord or rope. Sorda means thread, a concise rule, or aphorism. Together the Sulba Sordas were threads of knowledge, woven for those who built altars, guiding them with ropes and ratios, geometry without proofs, but not without purpose. And maybe that's what makes them feel so human. They weren't writing math for math's sake. They were building shapes to bring order to the cosmos. In these rituals, the shape of the altar mattered. A square might represent the earth, a circle, the sky, a falcon-shaped altar, flight, aspiration, transcendence. And so geometry became sacred, because space itself was sacred. But sacred doesn't mean simple. To transform a circle into a square of equal area, this was no casual task. To reshape a rectangle into a square, or construct an isosceles trapezium with precise proportions, this was real, tangible mathematics. And here's the quiet brilliance. They figured it out. Long before Euclid, long before formal axioms, using only ropes, pegs, intuition, and memory. There's a verse in the Baudhayana Sulba Sordas that reads, the diagonal of a rectangle produces both the areas which the two sides produce separately. It doesn't say a squared plus b squared equals sine c squared, but it's the Pythagorean theorem, written centuries before Pythagoras. You can almost see it, a right triangle, staked out with chord. One side 3 units long, another 4. The diagonal stretches across 5. 3 squared plus 4 fort equals sine 5. 9 plus 16 equals 25. Not by accident. By design. This was applied mathematics in the truest sense, not done on paper, but in dirt. Not proven with words, but trusted through repetition. Built, measured, real. And that's what makes it feel alive. These weren't abstract puzzles for mental pleasure. They were instructions for how to cut the universe into meaning. Sometimes the instructions are poetic, sometimes mysterious. One passage describes how to square a circle, an ancient problem later shown to be impossible with perfect accuracy. Yet they came close. So close that for centuries, no one noticed the approximation. And maybe that's the magic of it. This wasn't perfection in the modern sense. It was approximation with grace, elegance through limitation. When they transformed one shape into another, they weren't merely manipulating area. They were navigating between forms, between ideas. A square into a circle, a rectangle into a square, a rope into geometry. You can feel a kind of respect there, for space, for balance, for proportion. Even without diagrams, their instructions show a deep understanding of geometry as something both practical and profound. They teach how to create a square with a given side, how to construct right angles using chords stretched into triangles, how to build altars with hundreds of bricks, all laid in alignment with cosmic principles. And as we read them now, through translations and commentaries, we can't help but ask, how did they know? There's no answer really, just the work itself. And maybe that's enough, because the Sulba sortus remind us of something often forgotten in math, that it began with the body, with hands, with feet marking lengths, with eyes measuring lines, with ropes held taut, drawing the first ideas into the ground. It was lived before it was written, felt before it was formalized. Math wasn't always cold. It wasn't always abstract. Sometimes it was warm, sorta, shared. And when we revisit texts like the Sulba sortus, we don't just study what they did. We remember what math can be. A dialogue between the sacred and the structured, between form and function, between human instinct and eternal patterns. Even now, there's something soothing about that. The rope, the altar, the proportions, the patience. So if you ever feel that math is distant, or that it doesn't belong to you, remember the Sulba sortus. And remember this: a long time ago, someone stood barefoot on the earth, measured the sky with a cord, and built a square, not just to calculate, but to connect. Sangaku, Japan's temple math puzzles. Think about a quiet kind of beauty in a question that is left hanging. Not the frantic kind, the question that demands an answer, but the still kind, the kind that's carved into wood, left in the open air, and offered to anyone who feels drawn to solve it or simply sit with it. That's what Sangaku were. Wooden tablets, carefully painted, carefully hung under the eaves of temples and shrines in Edo period Japan. Some were small, others wide as a doorframe. But each one contained the same gentle mystery, a math problem, a puzzle resting quietly among incense and prayers. It might seem strange at first that math, something so often wrapped in grades and pressure, was once a kind of offering. But that's what Sangaku were. Not tests, not competitions. They weren't for praise, or for money, or even for publication. They were for the joy of the question itself, for curiosity, for reverence, for play. In the 17th century, Japan had closed its borders. It was a time of isolation. What historians call sakuku, Western science, ideas and influences were largely shut out. And yet, within that quiet isolation, mathematics bloomed. It wasn't the kind of math we associate with chalkboards and textbooks. It was visual, expressed in circles and triangles, inscribed into wood in neat black ink, surrounded by respectful brushstrokes and the occasional poetic dedication. Imagine standing under the eaves of a quiet shrine. You've come to pray, or maybe just to breathe, and then you look up and there it is. A puzzle, a circle within a square, touching other circles. A question: what is the radius of the smallest circle that fits between the others? No hint, no answer key, just the problem. A riddle hanging in stillness, written not to stress the mind, but to stretch it. There's something beautiful about that kind of offering. In Shinto shrines, people tied wishes to trees. In Buddhist temples, they bowed before statues, and in some corners of Japan, they gave math. They gave their time, their thinking, their care. And they didn't expect the puzzle to be solved quickly or easily. That wasn't the point. These were slow puzzles. They asked you to return again and again, to take your time, to see deeply. Sometimes the puzzles were practical, other times purely elegant. They showed a culture of math that wasn't just technical, it was spiritual. It didn't separate mind from heart. Solving a Sangaku was a kind of meditation, a kind of prayer. We often think of math as something cold, clean, mechanical. But for the Japanese mathematicians of the Edo period called Wazen scholars, it was anything but. They wrote with brush and ink, not calculators. They worked in courtyards and on tatami mats, not in labs. And they weren't solving for industry or invention. They were solving because it was beautiful to solve. In a time without mass education, Sangaku invited everyone in. Farmers, samurai, merchants, priests. Some were created by master mathematicians, others by anonymous visitors. Women, too, left puzzles, quietly, in a society that didn't always welcome their voices. The tablets held all of them, side by side, equal, in wood and ink. One of the most common themes in Sangaku is the circle, circles inside triangles, circles within squares, tangents, arcs, nested curves. It wasn't just for aesthetics, though the shapes were undeniably pleasing. It was about harmony, symmetry, balance. In Japanese art and architecture, nature is not conquered, it is mirrored, echoed. Sangaku reflected that too. Geometry wasn't a tool for control, it was a way to witness harmony already present in the world. To find the hidden pattern inside a branch, or a ripple, or a thought. Not all Sangaku survive, many have been lost to weather, war, or time. But hundreds remain, preserved in shrines, photographed, transcribed, studied by modern mathematicians who still marvel at the ingenuity of these centuries-old puzzles. Some of them are so complex they weren't solved for hundreds of years. Others remain unanswered. And maybe that's okay, because a Sangaku isn't just a problem to be solved, it's an invitation. An invitation to pause, to look closely, to work gently, to fall in love with something abstract and strange. To treat a puzzle not as an obstacle, but as a form of art, a quiet dialogue across time. So next time you think of math, don't think only of numbers on a page. Think of wood, ink, and brushstrokes. Think of a tablet hanging under temple eaves, swaying slightly in the wind. Think of someone long ago, standing beneath it, tilting their head, smiling quietly, curious. And maybe, just maybe, they weren't trying to solve it quickly. They were just enjoying the question. Napier's bones, the original calculator. What happens when numbers become physical? When calculation leaves your head and enters your hands? In the early 1600s, that question had a quiet answer, a set of narrow rods, each one etched with numbers. No gears, no springs, no electricity, just patterns, lines, and a way of thinking. They called them Napier's bones, but what were they really? And why did they matter? Let's start here. Imagine you need to multiply 467 by 8. Today you'd reach for a phone, or a calculator, or an Excel cell. But back then, you'd be doing it longhand, slowly, carefully, and probably with mistakes. So, how do you make multiplication easier without inventing a machine? That's the puzzle John Napier was working on. Napier was a Scottish mathematician, but also something else, a systems thinker. He believed that repetition wasn't just boring, it was solvable. He looked at long multiplication and saw a pattern. He thought, why can't we break this into parts? Why can't we build something that helps the eye do what the brain struggles with? So he designed a tool, a physical one. Dozens of thin rods, each one marked with a digit at the top, and a grid of multiplied values below. Each row split diagonally, dividing tens and units. When laid side by side, these rods could transform long multiplication into something almost mechanical, visual, predictable, tactile. So what did you actually do with them? You'd take the rods matching the digits of the number you wanted to multiply, say 4, 6, and 7, and line them up. Then you'd look across the row for the number you were multiplying by, say 8. You'd read the digits, follow the diagonals, and add along the lines. The product appears. No paper required. But here's the bigger question. Why does this matter? Because Napier's bones weren't just a clever shortcut. They were an early sign of something deeper, that computation could be externalized, that the act of solving could be split between mind and object. In a way, Napier was doing something radical. He was offloading cognition, putting part of the thinking outside the brain onto something you could hold. This may seem small, but it's the same principle that would one day lead to the abacus, the slide rule, the calculator, and eventually, the computer. Here's something else to think about. Why rods? Napier could have written a book, or made a chart, but he chose objects. Individual pieces you could move, arrange, interact with. There's a kind of intuition there. Something about the modularity of thought. When a problem is too big, break it into pieces, let the pieces carry the burden. The rods weren't just tools, they were interfaces, which brings us to another question. What does this tell us about the nature of tools? Good tools don't just do things faster, they change how we think, they reshape what feels possible. With Napier's bones, multiplication wasn't just faster, it was different. It was something you could feel with your fingers. And when thinking becomes physical, it becomes teachable, transferable, scalable. People across Europe used these rods. Traders, navigators, students, they didn't all understand the math underneath. But they didn't need to. They just needed to know how to lay the rods, read the diagonals, and trust the pattern. In that sense, Napier's invention did something subtle and profound. It separated logic from labor. It let the logic sit in the background, while the labor became mechanical. And that's something we still do today. Every time we swipe to calculate a tip, or drag a formula in a spreadsheet, we're using tools to stand in for understanding. Not because we're lazy, but because we've learned how to structure knowledge in reusable ways. Which leads us to the final question. What happens when you take something invisible, like multiplication, and give it shape? You change its relationship to the mind. You move it from abstraction into space. You give it edges, and edges can be touched, learned, improved. Napier's bones weren't flashy. They didn't go viral, but they were a turning point. They showed that even before circuits and code, we were already thinking like engineers. Already finding ways to let objects carry thought. Already building systems that let us step back and let the tool step in, not to replace the mind, but to extend it. The calculus controversy, Newton versus Leibniz. There's a certain stillness in the early hours of thought, a kind of silence that surrounds the moment before discovery. Not the bang of genius, but the quiet build, like mist forming over water. In the 1600s, two minds on opposite sides of Europe stepped quietly into that mist, one in England, one in Germany, both thinking about change, both wondering, how do you measure motion in a world that never stops moving? Their names were Isaac Newton and Gottfried Wilhelm Leibniz. You've probably heard of them, at least in passing. But this is not a story about names. It's a story about time, truth, and the strange way invention often walks in pairs. Let's pause for a second. When you hear the word calculus, what do you feel? A little tightening in your chest. Memories of homework, symbols, confusion, maybe curiosity, maybe dread. But beneath all the formal rules and strange notations, calculus began with something beautifully human. A desire to understand change, the speed of a falling apple, the curve traced by a comet, the way one thing becomes another. How do you study a thing that is always slipping away? That's what Newton and Leibniz were trying to answer. Newton came first, at least in silence. During the plague years of 1665 and 1666, when Cambridge University shut its doors, Newton went home to the countryside. In isolation, he began sketching out what he called the method of fluxions. He imagined quantities flowing, changing with time, and he tried to capture their motion as it happened. But he didn't publish. Not then. Not for years. Newton was cautious, private. He wrote for himself, not the world. To him, mathematics was not a conversation. It was a solitary climb into the mind of God. Leibniz, on the other hand, was a sharer. Curious, exuberant, multilingual, he lived in ideas like a bird lives in air. In the 1670s, he too began thinking about infinitesimals, tiny vanishing bits of change. And unlike Newton, he published. He created the notation we still use today. Dix, the differential, the integral sign, elegant and swooping like a stretched-out S, for summa, the Latin word for sum. Leibniz didn't just discover calculus, he made it beautiful. He gave it a language the world could use. And then there was friction. When Newton finally released his version of calculus, years later, his followers noticed something uncomfortable. Leibniz's work looked suspiciously familiar. Too familiar. Accusations began to surface. Had Leibniz seen Newton's unpublished notes? Had he taken ideas not his own? Leibniz denied it. Newton's supporters insisted otherwise, and thus began one of the most bitter disputes in the history of mathematics. The calculus controversy. At its heart, it wasn't just about who invented what. It was about ownership of thought. Can two people arrive at the same truth independently? Does discovery belong to the one who sees it first, or the one who shares it best? The Royal Society, led by Newton himself, conducted an impartial investigation. Their conclusion? Newton was the true originator. Leibniz had borrowed too freely. But the twist? Newton wrote the report himself, anonymously. He shaped the verdict on his own legacy. If this sounds petty, remember, these were not just scholars, they were humans, proud, brilliant, bruised. Newton had spent years in silence, haunted by doubt, afraid of critics. Leibniz had poured himself into language, beauty, communication, only to be accused of theft. They each held a piece of the puzzle. And the irony? Both were right. They had discovered calculus independently. Two different roads to the same mountain. Newton's method of fluxions focused on motion and physics. Leibniz's differentials were abstract, algebraic, easier to generalize. Today's calculus blends both worlds. And most modern mathematicians, if asked, will tell you, it doesn't matter who was first. What matters is that it happened. But there's something deeper here. A pattern we see in every field, every generation. Ideas often arrive more than once. Discovery is rarely a lightning bolt. It's more like a rising tide. No thought lives in isolation. And even when two people think they're alone in their insight, the world has often been preparing for it. Isn't that a kind of comfort? That we are not as separate as we seem. That the truth waits for whoever is ready to see it. So next time you see a Warner's in a textbook, or a curve being analyzed by Dykes, remember, that symbol carries history. Not just of Newton or Leibniz, but of the silence, suspicion, beauty, and brilliance that gave rise to it. And beyond all the controversy, beyond the ego and the argument, there was always a single quiet question. How does one measure the shape of change? Hilbert's 23 problems that shaped math. Have you ever thought about moments in history that don't feel like much until you look closer? A quiet podium, a lecture hall, a man standing in front of a chalkboard with a list. But that list, it changed everything. His name was David Hilbert. It was the year 1900, and the world was about to walk into a new century, still blinking from the discoveries of the last one. Radio waves were whispering through the air. X-rays were revealing what was once hidden beneath the skin. And mathematics, like everything else, stood at the edge of something vast and unknown. Hilbert stepped forward and offered something rare. Not answers, but questions. 23 of them. Not random curiosities. Not idle puzzles. But deep, sharp challenges, questions that reached into the heart of what mathematics was and what it might become. Questions that didn't just ask how to solve something, but asked what solving even means. That was the quiet brilliance of Hilbert's moment. He didn't shout, he pointed, and the world followed. At first glance, a list of problems might not sound all that revolutionary. But that's the nature of deep change. It often begins not with a breakthrough, but with a clear articulation of the unknown. Hilbert understood something essential, that math isn't just about theorems or numbers or formulas. It's a living structure of thought, a language for reality. And like any language, it evolves by confronting its own limits. He wasn't asking, what do we know? He was asking, what is still uncertain? What hasn't been built yet? What dreams lie just out of reach? Each problem on that list was a door. Some opened into realms no one had entered before. Others still haven't opened. A few may never. Problem 1. The continuum hypothesis. Is there a size of infinity between the counting numbers and the real numbers? It's a question that feels like touching fog. Your hand goes through, but the mystery remains. That one still echoes today, not because it hasn't been solved, but because of what its solution taught us, that even in math some truths cannot be proven. Some things are independent of the rules we set. That alone would have been enough to shake the foundations. But Hilbert's list kept going. Problem 6. Can all of physics be described by a system of axioms like geometry? A question not just for mathematicians but for the universe itself. Problem 10. Is there a method to decide whether any given polynomial equation has an integer solution? It sounds technical, maybe even dull, until you realize it's a question about the limits of logic, the boundaries of what's computable. Decades later, it would be proven unsolvable. And in that unsolvability, a new world of understanding began. But maybe what's most beautiful is not what these problems did for math, but what they asked of people. Because each one demanded something different: patience, creativity, humility, vision. Some of the greatest minds of the 20th century grew up in Hilbert's shadow: Gödel, Turing, Cohen, Nash, Grothendieck. They weren't just solving math, they were wrestling with the very edges of knowing. Hilbert didn't live to see them all answered or unanswered. But his voice still lingers in the way we ask our questions. His problems became not just goals, but mirrors, reflecting our desire to understand, our need to find order in chaos, to stretch thought as far as it can go. And here's something worth pausing on. Some problems from the list have clear final answers. Others led to entire new fields of study. A few dissolved when seen from a new angle. And some are still open, not because we haven't tried hard enough, but because they sit at the very boundary of reason itself. That's not a failure. It's the nature of deep inquiry. Sometimes the value of a question isn't in its resolution, but in what it awakens. So what do 23 problems mean today? In a world driven by instant results, by answers at the tap of a button, Hilbert's list is a quiet resistance. A reminder that not everything valuable can be rushed. That sometimes the most meaningful paths are the ones we walk without certainty. You don't need to understand every equation to feel what Hilbert gave us. He gave us a model for how to wonder well, how to take what we don't know and hold it up, not with fear, but with curiosity. That kind of wondering is slow, it's deep, and it's very human. So the next time you struggle to solve something on paper or in your life, remember this. The greatest mathematicians didn't always have the answers, but they were brave enough to ask the right questions, over and over. Across time, sometimes the question is the gift, and asking it is the start of something extraordinary. Gauss, the child prodigy. There are moments in history that don't announce themselves. No drumroll. No fireworks, just a quiet child in a quiet classroom doing something no one expected. Carl Friedrich Gauss was only a boy when it happened. Maybe 7, maybe a bit younger. The details blur across retellings, but the story lingers sharpened by how oddly gentle it is. A classroom, a teacher, tired. He wants silence. So he gives the students busy work, add all the numbers from 1 to 100, enough to keep them occupied for a while. But Gauss doesn't hesitate. He stares ahead for a moment, then writes down a single number, puts down his slate, and waits. The teacher looks up, irritated, suspicious, then sees the answer: 5050, perfect, instant, unbelievable. It's become legend, the moment the world met the boy who would one day be called the prince of mathematicians. But pause here. Not to admire the cleverness, not yet, just to notice how strange it is, this silent, internal moment, a small child doing what no one asked him to do, not adding, seeing a pattern where others saw a chore, because what Gauss understood wasn't just arithmetic, it was symmetry. He saw that 1 and 100 make 101, so do 2 and 99, and 3 and 98. a cascade of pairs, each summing to the same total, 50 pairs. Each one adding to 101. 50 times 101 equals 5050. That's not math like we're taught it. That's math as an act of noticing, of seeing through the numbers, and maybe that's what set Gauss apart, not just his speed, but the stillness he seemed to carry inside, as if numbers didn't live on paper, but floated somewhere behind his eyes, quiet, obvious, waiting to be arranged. But Gauss didn't start in comfort. He was born in 1777, in Brunswick, Germany. His family was poor, his father a laborer, money was tight. Education was not guaranteed, but his mind was already walking paths no one else could see. By the age of 3, he was correcting his father's arithmetic. By 5, he was fluent in calculation. But the gift was not just speed, it was precision, calmness, as if numbers bent themselves around him. And eventually someone noticed. A local duke funded his schooling. Teachers stepped back in awe. He entered the University of Göttingen as a teenager and soon delivered his first major discovery, one that had eluded mathematicians for over 2,000 years. The construction of a regular 17-gon. It sounds simple. It isn't. For centuries, no one knew whether it could be done using only a compass and straight tools the Greeks used, tools they revered. And then Gauss, just 19, proved it could. It wasn't just a proof, it was a message. This was someone who didn't just answer old questions, he found new ways to ask them. But let's return to the child for a moment. It's tempting to think of prodigies as freakish exceptions, minds so unlike ours that we can only admire them from a distance. But there's something in Gauss that feels quiet, accessible, not flashy, not chaotic, just clear. His genius wasn't loud, it was steady. And perhaps that's why his story feels so calm, even in its brilliance. As Gauss grew, he moved between realms, pure mathematics, astronomy, geodesy, physics. He charted the orbit of Ceres, a newly discovered asteroid, using only a few scattered observations. His prediction was so accurate that astronomers found it right where he said it would be. Again, not just calculation, clarity, insight, seeing structure where others saw fragments, and always he worked privately, carefully. Many of his discoveries stayed in his notebooks for years, decades, even lifetimes, only to be found later, long after his death, not because he feared error, but because he respected truth. He once said, "Few but ripe," that was his motto. Not volume, not fame, just depth. He treated each idea like something alive, something to be nurtured until it was whole. And maybe that's what lingers when we think of Gauss. Not just the brilliance, but the tone of it. The quiet child with the slate, the patient man with the telescope, the mathematician who saw shapes in numbers and certainty in silence. He reminds us that genius doesn't have to shout, it doesn't have to move fast or demand attention. Sometimes, it just waits until it sees the right pattern, and when it does, it moves, simply, clearly, like a hand reaching out across centuries, placing a number on a desk, 5050. Boole and the algebra of logic. Let's say you wake up in the morning and do something brave. You check your email. There it is. A flood of subject lines. Some you open, some you delete, some you leave in "I'll get to it later" limbo. And here's the thing. Every time you clicked, or didn't, your computer made a decision. It asked itself questions like, is this email marked important? Is this person a contact? Is this spam? And it answered those questions using something that has nothing to do with feelings and everything to do with a quiet little system from the 1800s called Boolean logic, which sounds intimidating, but don't worry, we're going to demystify it. By the end of this, you'll not only understand Boolean logic, you might even kind of love it. A little. No pressure. Let's meet the guy who started it all. George Boole. Now, Boole didn't live in the age of laptops or cloud storage or recommended YouTube videos about Boolean logic. He lived in Victorian England, wore long coats, and taught himself math. Not long division math. We're talking, I think I'll create an entirely new branch of mathematics math. And he did. Because one day George Boole had a thought. A weird, brilliant thought. What if we treated logic, the stuff we use to argue on the internet or decide where to eat dinner, as math? Pause. This might seem like a weird mashup. Logic and math. Aren't they already kind of cousins? Sure, but Boole didn't want to talk about logic. He wanted to calculate it. So here's the wild idea. Let's say you've got two statements. A, it is raining. B, I have an umbrella. Boole would look at those and say, great, let's represent true as 1 and false as 0. So if A is true and B is also true, then A and B is 1. If either is false, then A and B become 0. Simple, right? It's like logic but with snacks. By snacks, we mean math. Boole came up with ways to combine statements using basic operators, and both must be true. Or at least one is true, not the opposite of true. He created a whole algebra out of this. Like x plus y equals sine z, but instead 1 and 0 equals sine 0, 1 or 0 equals sine 1, not 1 equals sine 0. And you might be thinking, cool, George. But why would anyone need this? Excellent question. Boole probably wondered the same thing. Because when he wrote his book An Investigation of the Laws of Thought in 1854, the world wasn't quite ready. They didn't have microchips. They didn't have algorithms or databases. They didn't even have consistent indoor plumbing. But Boole kept going. He wasn't trying to change the world. He just wanted to understand how we reason, and whether that could be made precise. Spoiler, it could. It just took 100 years for everyone else to catch up. Fast forward to the 1930s. Enter Claude Shannon, MIT student and certified logic whisperer. He was studying how telephone relays worked. Basically electrical switches that turned things on and off. And one day Shannon looked at those switches and thought, wait a second, these are just 1s and 0s. And then wait another second, these behave just like Boole's logic. Cue light bulb moment. Shannon used Boolean algebra to design circuits, machines that could think in 1s and 0s, which meant machines could make decisions, which meant you could build logic into hardware, which meant computers. The thing is, your computer is really just a massive Boolean calculator. It asks questions all the time, but instead of asking them in English, it asks them in 1s and 0s. Is this file saved? 1 or 0? Is this key being pressed? 1 or 0? Should this cat video autoplay? Definitely 1. It's Boolean logic everywhere all the time. Let's try a real-life example. You're making dinner. You open the fridge and think, if fridge contains pizza and leftover tolerance, 0, then equal sign eat pizza. Else if fridge contains vegetables or guilt about health, 0, then equal sign make salad. Else equal sign order tacos. Congratulations, you're using Boolean logic, just with feelings. The beauty of Boole's system is that it turns fuzzy choices into crisp, structured ones. It doesn't solve your problems, but it gives your decisions shape. And that shape, it's now baked into nearly every system we use. Every search engine, every algorithm, every app that asks, would you like to allow this? Even databases ask Boolean-style questions. Show me all users where age, 30 and city equal sign Berlin. And at the deepest level, all our tech boils down to combinations of yes and no. Thousands, millions, billions of tiny electrical flips, happening so fast you never notice. All thanks to a 19th century math teacher who thought reasoning could be written like equations. Boole didn't get rich from this. He didn't get famous. He got pneumonia and died after walking through the rain to give a lecture. Seriously. But his ideas, they lived. They snuck quietly into wires and chips. They made their way into keyboards and browsers and voice assistants. They became the skeleton of digital thought. So next time you filter your emails, or tell your smart speaker to play jazz, or type cat or dog memes not sad into a search bar. Take a second to thank George Boole. He didn't just give us logic, he gave logic a language, and the world's been calculating ever since. Mystical numbers of the Pythagoreans. There was a time when numbers weren't just things we used, they were things we revered, not for what they could calculate, but for what they could reveal. The Pythagoreans believed numbers held secrets, not just to building or trading or measuring, but to reality itself. You've probably heard the name Pythagoras. Most people remember him from school. Triangles, formulas, geometry. But the man was more than a mathematician. He was part mystic, part philosopher, and he led a group of followers who didn't just study numbers, they listened to them. They believed that everything, music, the stars, the soul, could be explained by number and ratio, not figuratively, literally. One day, they were plucking strings on a lyre. They noticed something strange. When one string was twice as long as another, it made a sound that felt whole. When it was 2/3 as long, the sound shifted, but still felt pleasing. They began to notice a pattern. Simple, whole number relationships produced the most beautiful music. That's when the idea took hold. Harmony isn't just a feeling, it's math. They began to wonder, what if numbers don't just describe the world? What if they are the world? To them, each number had meaning. One was unity, the source, all things returning to one. Two was duality, light and shadow, male and female, tension and balance. Three was harmony, the beginning of structure. The first shape was stability, like a triangle. Four meant justice and grounding, the foundation beneath everything. And then there was 10. To the Pythagoreans, 10 was sacred. They had a symbol for it. A triangle made of 10 dots, stacked in rows, one on top, then 2 beneath it, then 3, then 4. This shape was called the tetractys, a word meaning fourfold. To them, this triangle represented all creation. Points becoming lines, lines forming surfaces, and surfaces building solids. A map of how something emerges from nothing. They would swear oaths to this shape, not to a deity or a flag, but to this quiet, perfect triangle of numbers. To us, this might sound strange, even superstitious, but think about it. When did numbers lose their mystery? When did they stop being magical? To the Pythagoreans, the world was full of invisible music. Stars made sound as they moved. They believed tones we couldn't hear but which shaped reality. They called it the music of the spheres. It wasn't science versus spirit back then. It was both, always both, and yet this beauty had a shadow, because one day, something didn't fit. A student of the Pythagorean school made a discovery. He was studying the diagonal of a square, and he realized something unsettling. There were lengths that couldn't be expressed by any clean ratio. No matter how he tried, no whole numbers could describe it. Today we'd call that kind of number irrational. But to the Pythagoreans, it was more than inconvenient, it was terrifying. Because if not everything could be explained through simple ratios, what else had they missed? Some say the student was punished, others say he was silenced. We'll never know for sure. But the idea left a mark. Still, they didn't stop believing. They focused on what still made sense. The patterns, the symmetry, the harmony. And maybe they weren't entirely wrong. Even today, we still talk about the beauty of symmetry, of balance, of proportion. When you hear a chord that just feels right, when a building looks perfectly shaped, or a painting gives you a strange sense of calm, you're feeling the same thing they chased. The world as music, the world as math, the world as meaning. The Pythagoreans weren't just solving equations, they were trying to understand why things feel right. And maybe they were onto something. Not because all their ideas were correct, but because they dared to look deeper. They saw numbers not just as tools, but as messages, symbols, keys. They believed that by living in harmony with number, you could live in harmony with life itself. That your soul, like music, could be tuned. They were seekers, not just of knowledge, but of resonance. So maybe the next time you catch your breath at a sunset, or feel goosebumps during a song, you'll remember them. Not because they had all the answers, but because they asked better questions. Because somewhere hidden in the spaces between numbers, between sound and silence, balance and chaos, they thought they heard the universe humming. And maybe, just maybe, you can too. Omar Khayyam's cubic classifications. A man sits alone under a pale domed sky. In one hand, a compass. In the other, a thought. His name is Omar. He is known for poems that wander through wine and time, but that's not what he's doing today. Today, he's drawing curves, not for art, not for beauty, but for answers. In his world, questions didn't come with symbols. There were no letters pretending to be numbers. There were no instructions typed into calculators, no graphs that appeared on screens. There was only the slow, careful shape of logic made visible. He was trying to understand something we now think of as ordinary, how to find a missing piece when the relationships become more tangled, when things are no longer simple, when a line no longer explains everything. He wasn't trying to predict the stars that day. He wasn't trying to write verses for lovers. He was doing something more patient, sorting. Imagine you've been handed a box full of puzzles. Some are missing corners. Some have extra sides. None come with a picture on the front. That's what Omar saw. Not one puzzle, but many. Not one kind of question, but 14. Each shaped slightly differently. Each needing its own way forward. And so he did what mathematicians in his time did best. He gave the questions form. He didn't plug in numbers. He didn't reach for a formula that hadn't been invented yet. He drew. He built bridges from one idea to another. He used circles to represent one kind of change. He used parabolas to represent another. And then he asked the oldest question in geometry. Where do they meet? That point, where one curve touches another, is the answer. Not in numbers. In place. In Omar's world, every unknown was a distance waiting to be seen. He didn't need to know what it was. He needed to know where it lived. There's something quietly radical about that. While later mathematicians would turn everything into abstraction, Omar was still working with earthbound shapes. He was building a map, not just of problems, but of how problems behaved. He looked at the different kinds of questions that could arise from this particular class of mathematical relationships, the ones that involved depth, volume, and change that bent more than it broke. And he sorted them. Each type had its own character. Some were missing middle steps, some were full, like a sentence with every part intact. Others were simpler, barely complete, but still meaningful. He identified what was possible, what could be solved, and what, at least for now, remained out of reach. You could say he was classifying relationships, the kind where balance isn't obvious, where one thing grows faster than another, where time and effort don't move in lockstep. There's something deeply human about that, trying to make sense of what grows wildly, what doesn't behave like a straight line. And maybe that's what Omar understood, maybe more than he realized, that some problems are solvable, if you can just step far enough back to see the shape of them, that even if the answer isn't easy, the path to it can be drawn. You just need to know which kind of curve to use. Not all questions yield to the same method. Some require softness, others precision. Some must be solved through contrast, one shape intersecting another in just the right way. That was his gift. He didn't find all the answers, but he found the categories. The architecture, the map. He knew which kinds of questions could be drawn into space, and that knowledge alone changed everything. Because after him, others came. They built on what he saw. They used his classifications as a foundation, adding tools, adding symbols, solving the puzzles he only began to sketch. But the roots, they were geometric, and behind those roots was a man with a compass in hand and a patient mind, tracing the hidden language of curves. There's something in that moment that feels familiar. We all try to classify the unknown in our own ways. We give names to feelings. make categories of our thoughts. We try to figure out what kind of problem we're in before we can begin to move forward. That's what Omar did too. He wasn't just solving, he was listening. And sometimes, when we step away from the machinery of modern knowledge, the speed, the calculation, the shortcuts, we can still hear it. That quiet invitation to trace the old path, to draw the curve, to meet the question in space, to find the point where understanding touches down. Baghdad's House of Wisdom. Baghdad. Not the Baghdad of today, shaped by headlines and history, but a different one. A city of gardens and shadows and libraries. A city that breathed ideas. It's the 9th century. The air is warm, and the world is quietly changing. In a quiet courtyard, scholars gather under latticed windows. They carry scrolls. They speak in Arabic, Greek, Persian, Sanskrit. They don't come to conquer. They come to translate. They come to think. This is the House of Wisdom, and it is exactly what it sounds like. Not a palace, not a school, but something else. A place designed for the patient work of understanding. In Arabic, it was called Beit al-Hikmah, a house, a home. For wisdom, it began under Caliph Harun al-Rashid and blossomed under his son, al-Ma'mun. But more than any ruler, it was the spirit of the place that mattered. There was no central doctrine, no rigid path, just the belief that knowledge, wherever it came from, was worth listening to. So they listened to the Greeks, to the Indians, to the Persians, to the stars. They gathered texts, mathematics, astronomy, medicine, philosophy, and translated them into Arabic. Not as copyists, but as collaborators. When a Greek term had no Arabic equivalent, they paused, thought, and sometimes invented new words, new ideas. Translation became transformation. Zero, for example, Hiver came from India, passed through Arabic, and moved west. The word cipher traces its ancestry back to this moment. So does the very concept of zero as a number, not just a placeholder, not just absence, but something, a nothing with presence. And with it came place value. That simple but profound idea, that the position of a digit changes its meaning. That 3 doesn't always mean 3. It might mean 30 or 300, depending on where it stands. That idea is invisible now, so woven into our systems that we forget it had to be discovered. But here, at the House of Wisdom, it mattered. Because once you understand place value and you allow yourself zero, something opens. Computation becomes elegant. Equations unfold, and suddenly math becomes a language that can speak not just of quantities, but of patterns. Movement, infinity. A Persian scholar named Al-Khwarizmi worked here. He didn't set out to change the world. He was writing a practical book on how to solve problems, inheritances, debts, measurements. He called it Algebra, the reunion of broken parts. We call it Algebra. His name Al-Khwarizmi was later Latinized into Algorithm. From that we get algorithm. From a quiet mathematician in a sunlit library, we get the seeds of modern computing. But if you're imagining rows of students and chalkboards, pause. The House of Wisdom wasn't formal. There were no lectures, no grades. Instead, it was a culture that valued long conversations, that respected silence, that saw no contradiction in translating an ancient Hindu text and a Greek philosophical treatise on the same afternoon. It was multicultural, interdisciplinary, fluent in contradiction, and that made it fertile ground for math, because mathematics isn't born in isolation. It grows when minds collide, when a geometry problem meets an astronomical puzzle, when a philosopher asks a question no one knows how to solve. Here, geometry wasn't decoration. It was a path to God. Algebra wasn't abstract. It was used to divide estates and build irrigation systems. Math lived. But more than the equations themselves, what survived was a mindset that no culture owns truth. That knowledge is a river, and every civilization adds to its flow. That idea feels rare now, but it was ordinary at the House of Wisdom. Books were treated like treasure, not for their beauty but for what they contained. A single translation could take months. One wrong word could change everything. So they worked slowly, together. And in that slowness, they built bridges. From Babylon to India, from Greece to Baghdad, from Baghdad to Europe. By the 12th century, these Arabic texts were translated again into Latin, and from there into the bloodstream of the Western world. When we study math now, we rarely trace the thread. We say Pythagoras, we say Newton, we say Euclid. But hidden between those names is a house. And in that house, quiet hands turned fading manuscripts into vibrant ideas. They copied, they argued, they invented. And in doing so they shaped the very language we use to think. You may never have heard of them. You don't need to. But every time you balance an equation, every time you write a zero, every time your phone runs an algorithm, you are walking, faintly, through the halls of the House of Wisdom. And in some quiet way, the house still stands. Not in stone, but in structure. Not in walls, but in the way we still believe that knowledge is worth sharing, that ideas are worth preserving, and that somewhere even now there is a place for wisdom. Decimal time during the French Revolution. There are few things more invisible than time. It's not loud, it doesn't flash, or knock, or shout, but it orders everything. Your mornings, your deadlines, your seasons, your sense of being late, or early, or right on time. And yet, this thing that shapes your whole life, this quiet scaffolding of reality, it didn't always look the way it does now. Not long ago, time itself was redesigned, not by nature, not by accident, but by people with pens and parchment and purpose, people who wanted to rewire the universe. This was revolutionary France, and they tried to change time to base 10. In the late 1700s, France was not just in political revolution, it was in ideological freefall. Monarchies were being dismantled, the church was being questioned, people were hungry, not just for food, but for clarity, reason, order. They believed the world had been distorted by superstition, so they turned to math. They wanted truth in numbers, structure in chaos, a new world designed like a clean equation. This wasn't just about government or taxes, it went deeper. They redesigned the calendar, replacing saints' days with days named after trees and tools and minerals. They abolished the 7-day week and replaced it with 10-day decades. And then they turned their eyes to the day itself. Why, they asked, should there be 24 hours in a day? Why 60 minutes in an hour? Why 60 seconds? These numbers didn't feel rational. They weren't base 10. They were relics, leftovers from ancient Babylonian math, where base 60 reigned. The revolutionaries believed a society built on reason should have a time system that matched their new decimal metric system. So they proposed something radical. Each day would have 10 hours. Each hour would have 100 minutes. Each minute, 100 seconds. A full day still had 24 traditional hours worth of time, but now it was divided differently. Each decimal hour was longer than what we think of as an hour. A decimal second, shorter than the one ticking on your wristwatch. At first glance, it's just a math trick, a unit conversion. But pause, and you'll feel something deeper. Imagine your morning routine, brushing your teeth, sipping your drink, checking your messages, now happening across a new clock face. Imagine work starting at 2:3 and ending at 7:6. No noon, no 3 p.m. Just decimal hours rolling across unfamiliar space. There's something eerie about it. Not scary, just quietly disorienting. Like walking through your childhood home and realizing all the furniture has been replaced. This was more than intellectual tidiness. To the revolutionaries, decimal time symbolized liberation. A break from monarchic time, from religious rhythms, from the sacredness of the number 7, from the old world's inherited structures. They were not just changing clocks, they were reprogramming reality. But reality pushed back. The new clocks were beautiful. Artists and watchmakers crafted intricate dials with 10 elegant hours and finely spaced decimal minutes. But adoption was hard. Daily life doesn't bend easily. Farmers still rose with the sun, not with decimal zero. Merchants struggled with scheduling, and no one wanted to count to 100 every time they boiled an egg. People were exhausted, emotionally, politically, mathematically. They were rebuilding a country, grieving, hungry, uncertain, and decimal time became one more adjustment in a sea of impossible changes. Even those committed to reason felt unmoored, because time is not just a system, it's a feeling. It's the background rhythm your body learns to trust. After just over a year, decimal time quietly disappeared from public life. It had been mandated by the state, printed on calendars, even taught in schools. But people let it fade. By 1805, it was officially abandoned. The clocks went back to 12s and 60s. The familiar tick returned, not because it was more rational, but because it felt more human. And maybe that's the heart of it. Sometimes, the most rational ideas don't survive, not because they're wrong, but because they don't resonate. There's a difference between what makes sense and what makes sense to live with. The revolutionaries believed they could measure the world into harmony. But time, like music, like memory, is more than just measure. It's a mood, a movement. And even in a world yearning for order, people still needed mystery. So next time you glance at a clock and see a 3 or a 7 or a 12, remember, there was a moment when the world tried to change all of it. To rebuild time from scratch, not to confuse, but to clarify. Not to disrupt, but to design. It didn't last, but it happened. And sometimes, even the things that fail leave behind the most beautiful questions. Cardano, gambler and probability pioneer. There's a moment at the table, dice in hand, breath held, the world waiting to collapse into a single number. And somewhere in the candlelight of the 1500s, a man named Girolamo Cardano is watching it all, half mystic, half mathematician, half gambler. Yes, that's 3 halves. But Cardano was that kind of man, too much for one life, never quite fitting the frame. He wasn't the kind of scholar you picture in silence, surrounded by scrolls. He lived loudly, played cards, made enemies, treated patients, told fortunes. A man who flirted with chaos and then tried to pin it down with numbers. And that right there is where probability was born. Not from a chalkboard, not from a lab, but from games, wagers, dice, and risk. From the sweaty palms of people hoping for a good roll. Cardano knew that world well. Gambling wasn't a hobby. It was a necessity. He was often broke, often brilliant, always chasing some combination of money, meaning, and pattern. And he noticed something. People thought luck was random, that fate had a personality, angry, moody, perhaps even fair depending on the day. But Cardano looked closer. He saw that not all outcomes were equal, that some bets were better than others, not because of hunches, but because of numbers. He began to wonder, what if chance isn't wild? What if it only feels that way when we're not paying attention? And so, quietly, while others played for coin, Cardano started writing. A book about games, about dice, about odds. A book he didn't publish in his lifetime, but one that would echo across the centuries. It was called Liber de Ludo Ali, the book on games of chance. And in it he did something astonishing. He treated randomness like it could be reasoned with. That was radical. At the time, there was no probability theory, no equations for risk. Fortune was still something people tried to charm or outwit. But Cardano said count, observe, calculate, don't guess. Add if a die has 6 sides and only one of them wins you the game. Then the chance of winning is 1 in 6, not because the gods say so, but because the shape does. Simple now, revolutionary then. And though his math wasn't perfect, and though he lived a life of mess and contradiction, Cardano planted the seed for a new kind of thinking, the mathematics of uncertainty. That idea would one day drive economics, insurance, weather forecasting, poker, stock markets, pandemics, and artificial intelligence. But it started with a man who bet on dice, and then asked, why does it work the way it does? Cardano's story is full of sharp turns. He was a licensed physician who treated patients for epilepsy and fever, but also believed in astrology. He claimed to predict his own death, and maybe he did. He also claimed his son poisoned his wife. He had enemies in high places and low ones too. He was jailed for casting a horoscope of Jesus. That's not a metaphor. He actually did that. And through all of it, poverty, loss, scandal, he kept calculating. His notes reveal the mind of someone who wanted control in a world that refused to offer it. That's what probability is, in the end. A way to measure the unmeasurable, not to predict the future exactly, but to know what futures are more likely than others. A way to say this is possible, this is rare, this is probable, this is near impossible, but not impossible. Cardano didn't finish the puzzle, but he gave us a corner piece. What's strange is how modern this all feels. We still wrestle with randomness, still hate not knowing, still treat chance like a personal insult when it goes wrong. We see patterns where there are none. We try to predict luck with superstition, like wearing a certain shirt or tapping the dice a special way. But deep down we crave what Cardano craved: understanding. Something to anchor us in the swirling. And that's what math does, when it's working well. It gives us a shape to lean on, even when the outcomes aren't certain. It helps us see that unpredictability isn't the same as chaos, that randomness isn't always random. It's just hard to see clearly without stepping back. Today, probability is taught in classrooms, coded into algorithms, baked into the way we live. But few people know its roots lie in the life of a flawed, brilliant gambler from Renaissance Italy. Not in certainty, not in clarity, but in the moment right before the dice land, in the breath before the outcome, in the mind of someone who asked, is there a pattern here, and stayed curious enough to find one. That's Cardano's legacy, not perfection, not clean equations, but the courage to question chance, and to find that even luck has structure if you know how to look. Where mathematics came from, before there were numbers, before chalk scraped across blackboard, before the word mathematics became sharp and formal in your mouth, there was something softer. There was Mathema, not a command, not a challenge, a whisper, that which is learned, not memorized, not forced, but learned the way light is learned by morning, the way rhythm is learned by walking, the way understanding arrives slowly, quietly, almost by accident. It began not in classrooms, but in the body. A gesture, a glance, a child holding up fingers to remember how many berries were his. It didn't come wrapped in symbols. It came in seasons, in the angle of sun over field, in the bones someone carved with tallies, to count time passing, to say this happened and this will happen again. That too was mathematics. You see, it never asked for perfection, only presence. It was never about getting it right, only about noticing the pattern and staying long enough to let it teach you something. The Greeks gave it a name, Mathema, but it had always been there. Long before them, long before writing, long before the world was bound in ink, still, they gave it structure. Euclid with his lines, Pythagoras with his tones, Plato with his stars. They believed that to know the universe was to tune yourself to something eternal, to step into order and feel its shape echo back inside you. Not cold, not mechanical, sacred. To them, mathematics was closer to music than machinery. To them, to learn, it was to remember something you already knew, but had forgotten. Like a song you've never heard but somehow hum perfectly. And maybe they were right. Maybe we do remember. Maybe that's why some things feel so obvious, so achingly precise, like the fact that a triangle always finds its way to 180 degrees, or that a circle will always carry its secret around in pi. Maybe it's not that we're solving the universe. Maybe we're recognizing it. Maybe learning is a form of remembering, and maybe that's all Mathema ever meant. The gentle act of coming home to an idea that already knew your name, but somewhere along the way, the softness hardened, the learning became measuring, the wondering became proving, The quiet became performance, and so many of us learned to fear it, to believe we were not good at it, to flinch at the word math as if it were a mirror, reflecting not beauty, but failure, as if understanding had a timer, as if learning had to be fast to be real. But the truth is simpler, the root never changed. Beneath the formulas, beneath the deadlines and tests and rules, there is still the original word, quiet and patient, that which is learned, and learning is not a race. It is a long conversation between you and the world, between your questions and the shape of things. Even now, when you count the seconds until something ends, when you split the check without thinking, when you feel something click in your mind and you know that fits, you are doing mathematics. Not just because you calculated, but because you noticed, because you stayed, because you listened. And when we remember that, math becomes something else entirely. Not a weapon of comparison, not a barrier of intelligence, but a language, a practice, a way of loving the world by learning how it moves. There is a reason we find it in music, in architecture, in the curl of a wave, in the orbit of a moon. There is a reason we say math is everywhere. It's not just because the world runs on it, it's because the world is it, and so are we. We are born with patterns in our breath, with symmetry in our faces, with timing in our laughter. We are not separate from this language, we are one of its dialects. And so when you sit with a problem, even the kind that makes your chest tighten, try this: don't rush, don't resist, don't run, just listen. You are not bad at this, you are only far from the original word. Walk back, return to the first meaning. Let the numbers stop being numbers and become little lanterns, showing you the shape of your own thoughts. That's mathematics. That's Mathema. Not the finish line, but the path. Not the answer, but the learning. And that's enough. Archimedes, forgotten calculus. There was a man, 22 centuries ago, who could see the infinite. He had no computers, no symbols for limits, no knowledge of Newton or Leibniz or anything that would one day be called calculus. But still, he saw it. His name was Archimedes. And if history had gone differently, if one manuscript hadn't been scraped clean and written over with a prayer, we might be calling his method the beginning of modern math. But we forgot. Not all at once, not like a book burning or a great flood. We forgot the way a house forgets a song that used to be sung in its hallway, quietly, by neglect, by time. Here's what he did. He tried to measure the immeasurable, a curve, a spiral, a surface bulging in space, the kinds of things you can't fold with a ruler or weigh with a scale. He asked, how do you know the area beneath a curve that never sits still? And then he sliced. He cut the space into triangles, slivers, tiny pieces, each one imperfect. But together, something strange started to happen. The chaos began to behave. The more pieces he added, the closer they came to the curve's true shape. Not exact, but close. And then closer. This sounds ordinary now. But think of it like this. You're trying to hug fog. You can't hold it, but you keep shaping your arms over and over until your outline matches what's there. That's what Archimedes did. With math, today, we call this integration. Back then, there was no word, only the act, only the seeing. He called it the method of exhaustion because he kept pressing the edges of the unknown until it gave in. But here's the thing. We all carry programming. Scripts written by time and culture, ideas of what's possible and what's not. And back then, the idea of using infinity, of approaching a solution by way of endlessly smaller pieces, wasn't just unfamiliar. It was unsettling, wrong even. The mind wasn't ready for that kind of thinking. Too fluid, too abstract, too ahead. So the world shrugged, and then it forgot. Centuries later, the story resurfaces. A book. A fragile manuscript. Not in a museum, but hidden inside a Christian prayer book. The original ink scraped away, the old words overwritten. But when scholars looked closely, Under ultraviolet light, the buried voice of Archimedes came through. And what they saw was astonishing. Diagrams, proofs, reasonings that mirrored the very heart of calculus. But from 1,800 years before Newton, as if a time traveler had dropped notes in the wrong century and no one noticed. We call them forgotten ideas, but really, they're paused ones. They wait quietly, for rediscovery, for attention. Archimedes didn't just anticipate integration, he felt it. This wasn't technical work. It was emotional, because to approach a curve this way is to say, I know I can't get there all at once. But if I keep moving closer, piece by piece, maybe I will. That's a kind of humility. And also a kind of courage. You do this too, you know. In your own life, you find yourself in patterns, big feelings, reactions that happen before you even notice. And then slowly, one moment, one decision, one pause at a time, you change the shape of your response. You approximate a different outcome. You begin to rewrite your code. Archimedes was doing that with numbers. He didn't conquer the curve, he partnered with it. Got as close as he could, then closer still, then stopped just short of perfection, and called that enough. He didn't need the final step. He trusted that if you move with intention, the shape will reveal itself. And that's what makes this forgotten calculus so human. Not the equations, not the diagrams, but the willingness to try, patiently, again and again, even when certainty is out of reach. That's not just math. That's attention. That's devotion. That's faith. When you zoom out, this story isn't about numbers. It's about time. How ideas surface when the world is ready. How genius can arrive too soon and be mistaken for noise. How knowledge can disappear and return when someone looks closely enough, like memory under scraped parchment, like shape beneath fog. There's a moment, late in his writings, when Archimedes describes the method he's using, not as proof, but as insight. A way of seeing, not calculating. Seeing, that's what makes it feel like now. Not ancient, not remote, but strangely modern, even urgent. Because if one person, long before the vocabulary existed, could dream a method into being, what quiet discoveries are being made today that no one's ready to name yet? What forgotten brilliance is waiting, buried, covered, erased, ready to be seen again? And how many of us, like Archimedes, are already slicing into the infinite, not to conquer it, but to understand it better? China's early use of negative numbers. Before there was a minus sign, there was color. Not ink on parchment, not equations in chalk, just rods laid gently on a wooden table. Red, black, positive, negative. Long before Western mathematics formalized what it meant to subtract a number from zero, someone in ancient China was already solving the puzzle, but they didn't argue about meaning. They didn't question whether less than nothing could exist. They just used it quietly, naturally, without fanfare. This was the 9 chapters on the mathematical art, a collection of methods written not to dazzle, but to serve. Somewhere between the 3rd and 1st century BCE, someone had already accepted what others wouldn't for nearly 2,000 years, that the world doesn't always add up in neat, clean positives. Sometimes it gives you less. Sometimes it leaves you owing. Sometimes it subtracts before you even know what was there. And instead of resisting that, they recorded it. They worked with it. They gave it shape and form and color. The black rods weren't just tokens. They were decisions. They were a way of saying, yes, this too belongs. When you owed a quantity, when you measured a loss, when you needed to balance what could not be seen, black rods stood in for the unseen. Not as errors, but as a kind of truth, because math for them wasn't an idealized structure hovering above the world. It was in the world. In rice stores and land surveys, in tax records and architectural plans, in trade and balance and change. Math was not theory, it was practice, and negative numbers weren't strange. They were useful, that made them real enough. Imagine the scene, a scholar seated cross-legged, a quiet room, sunlight drifting across bamboo rods. They're solving a system of equations, not with symbols or letters, but with arrangement, with color, with logic. A red rod says this exists, a black one replies, this is missing. And somehow between them, the truth emerges. Centuries later, when negative numbers reached Europe, they were treated with suspicion. They're absurd, said some. They don't exist, said others. Even in the 17th century, René Descartes, the father of analytic geometry, called them false roots. But China had already moved past that. Not with arguments, not with proofs, just with quiet use. They didn't ask, can this number exist? They asked, does this number solve the problem? And when the answer was yes, they trusted that. The beauty of the 9 chapters isn't in what it says loudly, it's in what it accepts silently. There is no dramatic discovery of negative numbers, no moment of invention. Only evidence of a worldview where absence has shape, where deficit is not denial, where something can be negative and still be real. They did not romanticize subtraction. They did not fear it, they simply worked with it. Because to measure anything honestly, you have to include the parts that are missing. You have to let shadows be part of the drawing. We forget how recent our understanding is. We think of negative numbers as obvious. But that's only because someone made them feel obvious. Because someone once believed that absence could be named. That minus is not a void, but a direction, a balance, a mirror. And that balance is where China's early mathematics shines, not in abstraction, but in reflection, in the belief that a number is not just what we see, but also what we owe, what we lack, what we must account for. So the next time you write a negative sign, pause. See it not as less, but as acknowledgement of what's been taken, of what is due, of what still counts. Even when it's missing, red and black, gain and loss, presence and space. This is the mathematics of honesty, of balance, of seeing the full equation, even the parts that don't stand in the light. Hypatia, the first known female mathematician. Let's start with something simple. What does it mean to be the first? We tend to think of firsts as beginnings, moments that lead to something larger. But sometimes, the first is also the last. A peak before a fall. A signal, not of progress, but of what's about to be lost. Hypatia of Alexandria was, by all available records, the first known woman to make a mark in the formal study of mathematics. And in many ways, she arrived at the edge of an era right before the lights went out. She lived in the 4th and early 5th centuries in Alexandria, Egypt. By then, Alexandria was no longer the fresh intellectual capital it had once been, but it was still powerful, still a place where knowledge lived in scrolls, taught in lecture halls, and carried in minds that questioned everything. This was the city of the great library, or at least what was left of it, and in this place, complex, unstable, deeply layered, Hypatia taught mathematics, astronomy, and philosophy, publicly, as a woman. In a male-dominated, increasingly politicized world, already that raises questions. How did she get there? The answer starts with her father, Than, a scholar and mathematician himself. He taught her, trained her, gave her access to a level of education most women of the time, and honestly most people would never receive. But it didn't end there. Hypatia surpassed him. She edited and refined some of his work. She taught in her own right, and not in secret, openly to students who traveled to Alexandria for her lectures. She wasn't just solving problems, she was shaping how people thought about solving them. She clarified the work of others, including Euclid and Ptolemy, and contributed to the understanding of geometry and astronomical systems. Let's pause here. In modern terms, you might think of her as a researcher, a professor, and a public intellectual. She worked on commentaries, she taught logic, she mentored students. She wrote letters that we still have fragments of tracing equations, correcting misunderstandings, reasoning through the nature of things. And all of this happened during a time when Alexandria was being pulled apart from the inside. The Roman Empire was declining. Religious conflict was escalating. Christians were rising in power, and tensions with both pagan and Jewish communities were growing rapidly. Hypatia, a pagan philosopher aligned with the Neoplatonist school, found herself increasingly isolated even as her influence grew. She didn't take sides in the political battles, but influence itself can be a liability. It's worth considering something here. She wasn't a threat because she led armies or because she sought power. She was a threat because people listened to her, because she represented the old world, rational inquiry, open discourse, the authority of the mind. And in unstable times, rationality can look like resistance. Eventually, those tensions reached a breaking point. In 415 CE, she was murdered by a Christian mob, dragged from her carriage, stripped and brutally killed. The exact motivations are debated. Some say it was political, others say it was personal, religious or ideological. Most likely, it was all of those, mixed into one moment of chaos, and that moment wasn't isolated. It was a signal. Her death marked something larger, the collapse of the classical tradition in Alexandria. After that, science and philosophy in the region receded. The lights dimmed, the memory of Hypatia faded for centuries. So now the question shifts: what do we do with a story like this? Do we treat it as a cautionary tale, a tragedy, a historical footnote? There's another option. We see it as a case study. Because Hypatia's life wasn't just rare, it was structurally unlikely. A woman in a hostile time, teaching advanced mathematics in public, and for a while, she succeeded. What allowed that? Access, mentorship, cultural space, and her own clarity of thought. And what ended it? Fear, power, politics, the inability of a society to make room for complexity. Hypatia didn't fall because her math was flawed. She fell because the world around her couldn't sustain the kind of mind she represented. But her work didn't disappear entirely. Fragments survived. Ideas passed through her students. Her name resurfaced centuries later, cited by Renaissance thinkers, Enlightenment philosophers, even modern scientists. She became a symbol, not just of lost knowledge, but of what it means to think clearly in a fog of fear. Today, we know more math than she ever did. We have better tools, bigger datasets, faster methods, but Hypatia reminds us of something we still struggle with. How do we protect the people who carry ideas? How do we value thinking when thinking itself is inconvenient? These questions don't have final answers, but they matter. Because every time a society begins to suppress its thinkers, you can find someone like Hypatia too early, too rational, too exposed. And every time a society begins to rise again, you can usually trace it back to someone like her, someone who believed that truth was worth pursuing, even if it came with risk. So maybe Hypatia wasn't just the first known female mathematician, maybe she was a prototype. A version of what happens when brilliance meets fragility, and also what's possible when teaching, curiosity, and clarity are allowed to exist, if only for a moment. The timeless abacus. There are tools that come and go, born from a need, used for a time, then forgotten. They rust, fade, get replaced. But then, there are the others, tools that linger, outlast generations, quietly outliving kings and countries, empires and algorithms. Not because they're the most powerful, but because they're the most true. The abacus is one of those tools. No batteries, no screen, no updates, just a frame, a few rods, some beads. And yet, it's still here, still used, still teaching, still solving, still reminding us that sometimes simplicity isn't weakness, it's wisdom. The first known abacus appears over 2,500 years ago, but even that feels like entering the story late. Because long before we had names for things, before math, before tool, Before even counting, we had problems to solve. How many animals did I trade? How much grain do I have left? What comes after 7? And out of that daily friction, we invented ways to keep track. Fingers first, then pebbles, then lines in dirt. Eventually, someone somewhere picked up a stone and slid it across a groove. A moment of clarity, a clean path, one object standing for one idea, a single bead, carrying the weight of a number, not because it had to, but because it could. The abacus isn't a single invention. It's a shared idea that appeared independently in different places: China, Mesopotamia, Rome, Japan. Some were made of bamboo, others bronze or wood, some vertical, some horizontal. The Chinese suan pan, the Roman hand abacus, the Japanese soroban. Different languages, different empires, same insight. We can move thoughts through space, slide meaning with our hands, and somehow that makes it easier to hold in our minds. At first glance, it looks like a toy, but spend a moment with it and something shifts. The bead moves. Your mind moves with it. Add 2, slide 1 down, 1 over, subtract, clear the board. Feel that. There's a rhythm here, a choreography of thought, a dance between hands and logic. The abacus doesn't just calculate, it teaches, not by giving answers, but by helping you see them form. There's no autocorrect, no shortcut. You can't pretend to understand. You either feel the numbers or you don't. And when you do, the beads almost move themselves. Today, children still learn math on an abacus. In some schools in Japan, it's not just a beginner's tool, it's a lifelong practice, because once you've used it long enough, the physical abacus becomes internal. Students close their eyes. Imagine the frame. See the beads move in their minds. This is called anzan, mental abacus. It's not memorization, it's simulation. Their fingers don't move, but the brain does. They can multiply huge numbers faster than calculators, not because they're faster thinkers, but because the tool trained their thinking. Why does something so old still work? Maybe it's because the abacus never tried to replace the human mind. It partners with it, supports it, and then, eventually, steps aside. Where a calculator hides the steps, the abacus reveals them. It doesn't give you the fish. It shows you how your hands already know how to swim. We often think progress means forward, newer, faster, smarter. But what if progress is also remembering what already worked? What if ancient isn't outdated? What if something built in silence, without screens or code or updates, could still hold its place in a world of machines? Maybe the abacus didn't survive by accident. Maybe it stayed because it still speaks to something we haven't outgrown. Our fingers want to move, our minds want patterns, and our hearts, whether we admit it or not, still crave that feeling. A simple, elegant solution, held in the palm of your hand. Sometimes when the modern world gets loud, it helps to go back. Back to the beads. Back to the frame. Back to a time when numbers weren't intimidating. They were visible, touchable, real. The abacus won't make headlines. It doesn't promise productivity hacks or cloud syncing, but it offers something rarer: focus, presence, and a deep, quiet reminder that even in a world of quantum computers and artificial intelligence, there's still something profoundly human about sliding one bead, and then another, and knowing exactly what that means. Logarithms and the stars. At the start of the 17th century, astronomy was on the edge of a breakthrough, but the tools weren't keeping up. The sky was being observed more precisely than ever before. Tycho Brahe had built the most accurate catalog of planetary data by eye, and Johannes Kepler was attempting to decode the motion of Mars using that data. But there was a problem, and it wasn't just the science, it was the math. Calculating planetary positions meant endless multiplications and divisions. Long, handwritten, multi-digit arithmetic that filled pages and drained time. One mistake, and the whole model broke. It wasn't elegant, it was exhausting. Enter John Napier. He wasn't an astronomer, not a physicist. not even a full-time mathematician. Napier was a Scottish landowner and theological thinker with a sharp mind and an unshakable question: could arithmetic be simplified? More precisely, could multiplication be done using addition, division using subtraction? It sounds like magic, but Napier found a method. And in 1614, after years of personal study and strange mathematical exploration, he published Mirifici Logarithmorum Canonis Descriptio, a description of the wonderful canon of logarithms. This wasn't just a book. It was a shortcut to the universe. Napier's invention, logarithms, allowed mathematicians to convert complex multiplications into simple additions by looking up values in a table. Instead of calculating, say 1327 quater 982 by hand, you'd look up their logarithms, add those, and then take the antilogarithm of the result. The multiplication was done indirectly, but faster, and with far fewer errors. For astronomers like Kepler, this was a revelation. Kepler, deep in his struggle to make sense of planetary motion, had already spent years drowning in numerical work. With Napier's logarithms, what once took hours could now be reduced to minutes. He quickly adopted the method, praising Napier's work and helping popularize it across Europe. But here's the deeper story. This wasn't just a time-saving trick, it was a paradigm shift. Logarithms changed the structure of how people thought about numbers. They introduced the idea that numerical relationships could be transformed, compressed, without being lost. They turned raw computation into navigable terrain. They offered an entirely new way to approach complexity. To understand why this mattered so much, remember, astronomy isn't just observation, it's prediction, and prediction is math. Kepler was trying to define the shape of planetary orbits. Copernicus had said they were circular. Kepler suspected they were elliptical, but to prove that meant working through reams of tedious calculations with Brahe's raw data. Without a tool like logarithms, the sheer arithmetic might have obscured the truth. With Napier's method, the calculations became feasible. And from that feasibility came discovery. Kepler's laws of planetary motion, his 3 rules that describe how planets orbit the sun, were born not just from insight, but from tractable math. And the tractability came, in part, from Napier. This was the real impact. Logarithms changed what was possible to do with knowledge. Soon slide rules were invented, mechanical devices that used logarithmic scales to help scientists, engineers, and navigators perform quick calculations. These tools would persist into the 20th century. For centuries, if you were working on the frontier of science, you were likely doing it with logarithms nearby. The irony is that logarithms themselves are abstract. Most people never see them clearly. We learned that the logarithm is the inverse of exponentiation. Log array 1000 equals sine 3 because 10 array equals sine 1000. Simple enough. But that simplicity hides something profound. Logarithms represent scaling. They translate multiplicative growth into linear space. They flatten exponential curves into straight lines. This is more than useful. It's intuitive if you learn to see it. In astronomy, where distances, masses, and timescales balloon to unimaginable sizes, logarithms gave people a handle, a way to compress the cosmos into something manageable. They didn't shrink the universe, but they gave us a better ruler. Even today we use them everywhere, in measuring sound decibels, acidity, pH, earthquake strength, Richter scale, even the brightness of stars' magnitudes. Anytime numbers grow too large, or change too quickly, logarithms are there to make sense of the mess. But it started with one question, one idea, in one mind. Napier didn't solve astronomy. He didn't discover a planet or invent a telescope. What he did was subtler. He changed the mental tools we use to engage with the world. And in doing so, he gave astronomers like Kepler the ability to ask and answer harder questions, questions about the shape of space, the rhythm of orbits, the design of the solar system. All because a man in a Scottish castle thought numbers might have a better way to behave. Peano's axioms. Okay, imagine you're in a universe where nothing exists. No apples, no clocks, no phone notifications, no math teachers, just pure, undiluted nothing. Welcome. You're now in the birthplace of numbers. Now ask yourself, how do you count in a place like this? Answer, you don't. Not yet. But what if you had to? Like if a bored cosmic entity trapped you here until you invent arithmetic from scratch, you'd need to start somewhere. And luckily, math has a plan for that. It's called Peano's Axioms, a short list of 5 ideas that somehow birth every single number, all operations, and basically all of grade school math. It's like Lego for logic. Let's start with the first brick. Axiom 1. 0 is a number. That's right, 0. Big round nothing. This is your starting point. No sheep, no coins. Just the concept of absence. Somehow that counts. Now you might say, great. We've invented nothing. That's progress? Hold on. Because Peano's genius move was saying, okay, from this nothing, let's define something new. Axiom 2. Every number has a successor, which means if we have 0, we can define a thing called the successor of 0, which we'll call 1. We don't explain what 1 inch is, we just say whatever comes after 0. Now take the successor of that, and boom, 2. Do it again. 3. Again. 4. This continues until your brain melts or your cosmic captor is satisfied. We're building numbers, one at a time, out of air. Axiom 3. 0 is not the successor of any number. Translation. You can't count backward into 0. Nothing comes before it. So don't try to sneak negative numbers in through the back door. Peano's got locks on that. Now let's say you and I both come up with 2 numbers that have the same successor. Like I say the successor of my mystery number is 3, and you say the successor of your number is also 3. Then Peano goes Axiom 4. If 2 numbers have the same successor, they must be the same. No duplicates. No cheating. The number line is strict. This keeps things from going all quantum spaghetti. And finally, the crown jewel. The axiom that powers mathematical induction, aka Axiom 5. If something is true for 0, and true for the successor of every number it's true for, then it's true for all numbers. It sounds abstract, but this is the reason we can prove anything about numbers forever, without checking each one. Like if you can prove a domino chain starts falling from the first one, and every domino knocks over the next, then you don't need to check domino hash 98,000. You know it'll fall. That's induction. That's Peano's secret weapon. Now you might be thinking this all seems really basic, and yes, that's the point. It's deliberately basic. This isn't about calculating your tax return or solving equations. This is about what numbers are. Think of numbers not as symbols, but as relationships. 0 exists. Then something comes after 0. Then something comes after that. Each number is just a new name in a long orderly queue. No pushing, no duplicates, no cutting in line. And from that tiny idea, succession, you get all of arithmetic, addition, just repeated succession, multiplication, succession within succession, exponents, succession riding on the shoulders of more succession. It's turtles all the way down. Here's what's wild though. Peano's axioms don't define the number 7 by showing you 7 apples. They define it by showing you the logical path you must take. 7 steps from 0. That's all 7 is. Math, at this level, doesn't care what numbers look like. It only cares how they connect. And that's kind of beautiful, right? It means that all the stuff we do with numbers, from tips at restaurants to rocket trajectories, is built on a ladder of logic that starts with 0 and climbs one rung at a time. And none of it depends on your intuition, only on the structure. Let's get existential for a second. Your reactions, your habits, your identity. You might think they're all spontaneous, but just like numbers, maybe you're running on axioms too. This is who I am. This is what comes next. This is what I have to do. Maybe those were written long ago, and you're just following the logical successor of some invisible script. But if math can rebuild everything from zero, maybe so can you. Not with emotion, with structure, not with drama, with clarity. The first rule: define your zero, then decide what you want the next thing to be. You don't need to know what 100 looks like, just the first step. Because once you set the logic, the rest follows. Galois. What happens when the future arrives too early? Suppose a thought appears in the wrong century. Not a full idea, not something polished, just a fragment, a flicker of structure. A new way of seeing hidden relationships where no one was even looking. What happens? Maybe it's ignored, maybe it's ridiculed, or maybe, just maybe, it's scribbled into a notebook the night before its creator dies in a duel at 20 years old, and left behind like a time capsule no one can open. Not yet. That was Évariste Galois. And this is a story about ideas that don't wait their turn. About a brain that tried to speak mathematics 50 years too early, and a world that didn't know how to listen. Let's pause here, because it's tempting to romanticize someone like Galois, the tragic genius, the mathematical martyr. But what if he wasn't a martyr? What if he was just a strange loop, a kind of recursive accident where a human mind accessed the future by mistake? He was born in 1811, in post-revolutionary France, an era vibrating with ideals and instability. You could go to a public lecture on symmetry one day, and a protest the next. He did both. By the age of 17, Galois had found a problem, or maybe, more accurately, he'd found a flaw in the way people solved problems. Mathematicians were still wrestling with polynomial equations, trying to find general solutions with the tools of the day: roots, substitutions, long division of logic. But Galois asked a stranger question. What if the solution isn't the point? What if the real story is underneath, hidden in the symmetry of the equation itself? This wasn't normal teenage behavior. It wasn't normal mathematician behavior either. He wasn't just solving, he was inventing a lens. Group theory, they would call it later. But at the time, it looked like gibberish. The academic gatekeepers, older, slower, more careful, rejected his work, or lost it, or misunderstood it completely. He was too fast, too abstract, too unwilling to translate himself. Which brings us to a different kind of question. How many geniuses never get heard because their ideas don't fit the mental furniture of the era they're born into? Galois wasn't quiet about his misfit status. He was politically radical, a revolutionary. He wore it like a badge. He got arrested, expelled, fired up. But through all the noise, the math kept happening. Then, just days before he was due to face a duel under mysterious circumstances, he knew this was it. And so, he stayed up all night and wrote. Not a goodbye, not a will, but an explosion of ideas. He poured out the beginnings of modern algebra, this concept that symmetries, not solutions, held the key to understanding solvability. He drew invisible shapes in conceptual space and asked what transformations leave this structure unchanged. You don't need to follow the math to understand the audacity, because what he really did, in those pages, was answer a question no one had properly asked yet. He gave a theory to a future that wouldn't recognize it for decades. Then he died. Here's the odd part. The work didn't vanish. It waited. It waited in envelopes, in attics, in half-read letters, until mathematicians decades later began to notice the bones of something they could finally understand. And when they looked closely, they didn't just see equations, they saw a framework, one that now sits at the heart of modern mathematics: physics, cryptography, coding theory, particle physics, and more. Group theory is the quiet operating system behind how systems behave, when they change, and when they resist change. Galois didn't just give us new answers. He gave us a way of asking questions we didn't know we were allowed to ask. So now we have to ask one more thing. What do we do with minds like his? When someone burns that bright, That early, do we build better institutions to catch them? Do we create faster translators between genius and structure? Or do we simply accept that some thoughts are born into the wrong decade and hope history has the patience to retrieve them later? Galois' life is a paradox. It's too short to be real, too impactful to ignore, too misunderstood to celebrate properly. And yet, undeniably, he left a fingerprint on the laws of logic itself. Maybe the question isn't how Galois died. Maybe it's how the idea survived him. How an insight scribbled under the pressure of time, in the margin of a desperate moment, could leap over generations and land in the architecture of everything. That's what makes Galois so strange. He wasn't solving today's problems. He was whispering to the future, and eventually the future answered back. The interest that didn't stop. There's a story about a man who asked a simple question. Not a philosopher, not a monk, just a mathematician wondering about money. His name was Jacob Bernoulli, Switzerland, 1600s. And what he wanted to know was this. If I put one coin in the bank and it earns interest, how much do I have after a year? Now, let's pause. This doesn't sound like the kind of question that leads to a breakthrough. It sounds like something your accountant might mumble while stirring sugar into their coffee. But sometimes, big discoveries come from small, annoying curiosities. Bernoulli wasn't just asking how money grows. He was asking how fast can it grow if we keep reinvesting the growth itself. It's what we now call compound interest. And here's the thing about compound interest. It's patient, it's quiet, and it's relentless. Let's say the bank gives you interest once a year. Simple enough. But what if they gave it to you twice a year, or every month, or every second? What if they gave you interest on your interest on your interest endlessly? That's where things start to stretch. Bernoulli ran the numbers. He noticed something odd. No matter how often he compounded, the total didn't explode. It didn't double or triple into chaos. Instead, it curved and began to lean toward a very specific number. It was like watching a plant grow faster and faster, but never out of control. Always curling toward something steady, a limit. That limit, though he didn't know it at the time, was E. Not a letter, a number, about 2.718. But we promised no equations, and we'll keep that promise. This number E is now one of the most important constants in all of mathematics. It shows up in growth, decay, probability, physics, biology. It's quietly everywhere. But it was born from this, a man wondering what happens when things grow on top of their own growth. And that's what makes it interesting. Because E isn't just about money. It's about feedback. It's about momentum. It's about the idea that the next moment isn't starting from scratch. It's starting from everything that came before, like a snowball rolling downhill, like trust in a relationship, like a bad habit or a good one. Once it starts compounding, it builds faster than you expect. Bernoulli's little banking experiment turned out to be a window into something universal, how systems evolve over time when their output loops back in as input. That's a big thought. But it's also very human, because we all have compounding in our lives. You say thank you once, it's polite. You say it every day, with meaning, and you build a foundation of gratitude. You skip the gym once, no problem. Skip it every day, and your energy slowly dissolves. The difference is often invisible at first. But compound interest doesn't care about how things feel. It just runs its course. Slow, then fast. Then faster. That's how EE works. It's not a number you meet with a bang. It's a number you grow into. You feel it when your investments start to accelerate. When your skills suddenly click after months of quiet practice. When a small daily choice becomes a major shift in who you are. And the beauty of EE is that it gives a shape to that journey. It tells us yes, if you let something build on itself, it won't just grow, it'll transform. Not overnight, not dramatically, but unavoidably. Here's the twist though. Bernoulli didn't get to see just how important EE would become. He didn't see it in probability theory, or population models, or neural networks, but he did understand its magic. He understood that when you allow something to grow continuously, and you fold its growth back in, you end up with a curve that moves like life itself. In fact, he was so moved by this discovery that he asked for it to be carved on his tombstone. Not the number E, not a formula, but a spiral representing exponential growth, a shape that expands forever, always reaching, always becoming. That's what compound interest gave us. Not just a better way to do math, but a deeper way to see the world. So the next time you hear the word interest, think bigger. It's not just about banks. It's about how actions stack, how habits ripple, how love deepens, how fears grow if left unchecked, how forgiveness multiplies if practiced often. It's about the long game, the invisible curve, the number hidden inside the motion of becoming. It began in a question about coins and ended in the architecture of growth itself. The many collaborations of Paul Erdös. Paul Erdös didn't own a home. He didn't drive a car. He never married. He had no fixed address. He floated from one university to the next, one friend to another, carrying only a suitcase, a notebook, and a hunger for problems. He called mathematics his religion. He called children epsilons. He said when he couldn't think clearly, it was because the noise was blocking his mind from accessing the book, a mythical tome, he imagined, where God had written the most beautiful proofs. And yet Erdös wasn't solitary. In fact, he may have been the most connected mathematician who ever lived. He wrote over 1,500 papers in his lifetime, but more remarkably, he did so with more than 500 different collaborators. Each conversation, each visit, each shared meal often turned into a shared theorem. To Erdös, collaboration wasn't a strategy, it was a way of being. He didn't just solve problems, he invited people into the solving, like someone offering you tea, then asking, "Have you thought about this?" Imagine that, math not as isolation, but as invitation, not competition, but companionship. He'd show up at your door unannounced, eyes bright, suitcase in hand, and ask, "Do you have a problem?" And if you did, he'd stay. For days, sometimes weeks. He might sleep on your couch, scribble on your walls, pace your hallway at night, muttering primes and conjectures. Then one morning, while stirring sugar into tea, he'd say, "I think it works," and just like that, another paper was born. Your name's linked forever. In the strange poetry of academia, this gave rise to something unexpected, a kind of mathematical family tree. People began to track how far they were from Erdös, not in geography, but in collaboration. If you had written a paper with Erdös, your Erdös number was 1. If you wrote with someone who had written with Erdös, your number was 2. If you wrote with someone who wrote with someone who wrote with Erdös, you get the idea. It was a joke, a game, but like many games, it revealed something quietly profound. It traced a hidden web through the world of mathematics, a constellation of minds, connected not by blood or nationality, but by shared curiosity. And here's what's worth noticing. Erdös didn't invent anything monumental. He didn't change physics. He didn't build a new kind of geometry. What he did was subtler. He connected things. He made bridges out of questions. He carried old problems across continents and gave them new eyes. He gave young mathematicians permission to wonder and old ones a reason to keep thinking. His genius was generosity. But even generosity has a rhythm. Erdös lived in motion. He thrived in discomfort. He didn't rest easily in comfort or predictability. Friends recall how he couldn't sit still unless a problem was being worked on. His mind always buzzing, always reaching. And beneath it all, maybe was a kind of avoidance. He admitted he didn't understand emotions the way others did. He once said he had no talent for life, only for mathematics, and yet what a life it was. He died in 1996 at a math conference in Warsaw. He had just given a talk. He was still working, still traveling, still asking, "Do you have a problem?" After his death, people looked back at the map he helped draw, this invisible lattice of minds and papers. A structure made not of steel or code, but of shared attention. And in that network, something beautiful appeared. Even now, decades later, you can trace your way back to Erdös. Maybe your math teacher studied under someone who had a professor who had written with Erdös. Maybe 5 steps, maybe 6. Not because he sought fame, but because he loved the game. And isn't that a strange kind of immortality? Not a statue, not a single equation, but distance itself becoming a form of belonging. The closer you are to Erdös, not physically, not temporally, but collaboratively, the closer you are to a tradition of minds reaching across time and language to chase something true. He once said, "Another roof, another proof," and maybe that was the essence of him. Always moving, always looking for someone to think with. Not for credit, not for money, just for the quiet joy of asking a better question. And so the man who owned almost nothing, who stayed nowhere for long, who preferred chalkboards to titles, left behind one of the largest footprints in all of mathematics. He didn't want to be remembered, he wanted the math to live, and maybe that's exactly what makes him unforgettable.